So in this video, we're going to start our LangGraph series by understanding what is an agent in LangGraph. What is a LangGraph agent? Now, the LangChain team created LangChain so that you can be able to work with, or rather build AI workflows, LLM-powered applications. So LangChain is basically based on workflows. But then AI agents became medium of value to deliver value with AI or specifically LLMs. And today we are hearing of AI agents everywhere. Salesforce recently talked about placing 4,000 roles with AI agents. So people are really taking AI agents serious. And the LangChain team obviously saw this. And because of that, they created LangGraph. Now, the purpose of LangGraph was to actually move all the agent development capabilities in LangChain into a specialized framework. So LangChain actually had tools for you to develop agents. There's even a create React agent in LangChain. But then because AI agents were becoming very, very popular, the team at LangChain felt it was very, very important to actually create a framework specifically designed for designing agents. And that is why we now have LangGraph. And in today's video, we're going to be looking at what an agent really means in LangGraph. So let us head over to our whiteboard. Now, in LangGraph, an agent is basically an autonomous unit that can reason through tasks and take some actions, then come to a final result. So you have specialized agents. The agent is meant to perform one task. That is, if you're not in a multi-agent system, which LangGraph can also do. But for now, let us just look at one agent. Let's look at agents in terms of one agent. So it is a specialized autonomous unit that can take a task, reason through it, that is break it down through chain of thought prompting, and then determine whether it should take actions. And after a series of actions, if it's able to come to the eventual result, it then terminates. It terminates. But let us look deeper into how agents in LangGraph work. Now, in LangGraph, agents basically consist of three parts. We have the LLM. The LLM is basically responsible for the thought process. So the LLM is the brain of the agent. The LLM is the brain of the agent. It's the one that reasons through tasks. It takes its tasks, it breaks it down, and reasons through it through, most of the time, a thought, action, and observation sequence, which we're going to talk about later. So we have the LLM, which is the brain of the application. Then next we have tools. We have tools. So we have tools and we have the LLM. And most of the time, people believe that these are basically the two things that make up an AI agent. Like LLM plus tools equals AI agents. And I think in its most basic form, that is what AI agents are composed of. LLM plus tools. But then, we also have a third part, which is the prompt. So we have the prompt. And the task of the prompt is to give instructions to the agent. So the prompt is how you communicate with your AI agent. The prompt is how you tell it the task you want it to perform. And then it's going to use the LLM to break down the task and then reason through it through a cycle. And then within that cycle, it can determine whether it should use some tools or not. So this is the simple way an agent works in LangGraph. But let us look at how agents go through this cycle. Basically, one thing you should put in your mind is that in LangGraph, an agent is basically an LLM in a loop. An LLM in a loop. That's basically what an agent is. But let us look at what that loop looks like. Let me put this up here. So prompt, LLM, tools. Those are the three parts of an agent in LangGraph. But how does an agent operate in LangGraph? So what happens is, first, you give it a task. So you give your agent a task. It then takes the task and reasons through it. So it reasons through the task. Takes the task and it reasons through the task. So that is, it breaks it down. It takes the task and breaks it down. So let's say you tell it to send an email. Then it will tell itself, okay, first I need to know who to send the email to. So it can prompt you to get the name of the person or the email address of the person you want to send the email to. Then it then says, okay, now I need to construct the email. Then it constructs the email. Once it constructs the email, you can add an extra step to say it should walk through the email and check it out and see that everything is fine. It looks at that, everything looks fine. Then it then goes again, and now I need to send the email. How do I send the email? Oh, I need to call a tool to send the email. So it calls a tool, and the tool sends the email. It gets a response back, which is mostly called an observation. Then it goes on like that. So once it reasons, it then checks whether it should call a tool. So should I call a tool or not? Most of the time, it will call a tool, especially when it has to make real world impact or read files or read data from somewhere. It calls a tool. And once it calls the tool, it then gives the tool to a tool executor. Let me get some arrows in here. So from reasoning to tool, and from tool to tool executor. So the executor executes the tool. It then sends back the results of the tool. Then the results of the tool are basically called an observation. So the agent is going to look at those results and see whether it has met the completion requirements. What are the completion requirements? It has to check whether it has met the completion requirements. Now, if it has not met the completion requirement, it then takes the observation, which is the result of the tool call, takes the observation, looks through the observation, and then uses it to determine the next course of action. That is by going back to this reasoning step. So it goes back to this reasoning step and goes through the loop again. So it goes through the loop over and over, and every time it gets the observation, it would always check. It would always check if it has met the completion requirement. To always check if it has met the completion requirement. So basically what happens is that it takes a task, it reasons through it by breaking it down. It then takes step 1. It checks whether it needs to call a tool. If it needs to call a tool, it gives it to the tool executor. The tool executor is going to operate and is going to return results, which are called observation. Now, when it checks the observation, it's going to check if the observation or the results of the tool call meet the completion requirement. If it doesn't, it will go back to reasoning. And it just continues to go through those steps one by one until it is able to meet the completion requirement. So that's why I said agents in LangGraph are basically an LLM in a loop. So basically that's how agents work in LangGraph, as we've seen. Let's give this color. Now, what are some of the other components of an AI agent? Like I said, in its most basic form, in LangGraph, an AI agent simply consists of a prompt, an LLM, and tools. The LLM is the brain, the tools are the action takers, and the prompt is how you pass instruction to the agent. But what are other components that that LangGraph provides? First is memory. So we have memory, and this memory can be divided into two. We have short-term. So the current session of the AI agent is what is called the short-term memory. That the current session in which the agent is in is what is called short-term memory. And when the agent operation terminates, that memory is gone. So it's transient memory. That memory is gone once the agent operation terminates. However, if the agent needs to reference memory that needs to be stored somewhere, then it has to make use of long-term memory. Long-term memory. So it needs to make use of long-term memory. These include, let's say, semantic information about objects. Also includes data, maybe a user base, customer base, and stuff like that. These are things that you cannot just stuff all in the memory all in the short-term memory or the context window of the AI agent. So long-term memory is for any information that you need to persist, that the agent will always have to reference from time to time, while short-term memory is meant for the current operation of the agent. Think of it like your RAM and your hard drive. So your RAM is the short-term memory, while your hard drive is the long-term memory. So we have memory. That's one of the components you can also find in a LangGraph agent. And we have human in the loop human in the loop capabilities. Human in the loop capabilities. Now, human in the loop capabilities is the ability for the agent to pause operation, so that a human being, that is you or anyone using the AI agent, can actually intervene in the current action. Maybe it needs to send an email, then it asks you, is this email okay? Can I go ahead and send it? That is an example of a human in the loop operation. So you can then say, yeah, go ahead and send this email. So you can intervene for things like approval, like we just described. You can also intervene for things like correction. You can choose to like edit the email, edit some things in the email before it goes. And you can also just take over. You can also just take over and say, yeah, I will take it from this point. Thank you for drafting the email. You don't need to send it yourself. I'm going to send it myself. So for approval, for intervention, and also just to take back manual control, you can employ LangGraph's human in the loop capabilities in its AI agent. Another thing you get with LangGraph agent is streaming support. Now, while an agent is in operation, it will be very beneficial for you to see its activities, to in real time know what it's doing. So there are tools in LangGraph that will help you output things like tokens consumed, steps taken, the reasoning process. Like I said, there's a thought, action, observation pattern that these agents go through. Thought meaning that they look at the task and kind of break it down. Then they decide whether there's an action they need to take. If they take the action, whatever result comes from the action is called an observation. So they look at it, see if it meets the completion criteria. If it doesn't, it goes back to the thought step. So probably want to see those steps as the agent is operating. A lot of people want to see what is going on with the agent, or even log it. So you can stream those type of outputs. You can stream tool call results. You can stream model tokens and stuff like that, just to see how it's consuming tokens in between operations. So that's another thing that you get out of the box with LangGraph. Now, to wrap up this video, let us look at how you can build agents in LangGraph. Let's look at how you can build agents in LangGraph, because that's what we're here for, and that's what subsequent videos are going to be. That's what I'm going to be teaching in subsequent videos. How can you build agents in LangGraph? Now, there are two ways. You can either build agents using primitives, using LangGraph primitives, and for that, LangGraph provides the Graph API and the Functional API. And you can use either of each. Whichever one fits your style, you can go ahead with that. But there is a Graph API and there's a Functional API. We're also going to be treating them in upcoming videos. So the Graph API gives you things like nodes, edges, and helps you represent your agent operations in a graphical format. While the Functional API is more similar to typical programming, how you typically program imperatively. So those are the two ways to use primitives. And these ways you can build your agents from scratch. You can build your agent operations from scratch. That is why LangGraph is the most customizable agent framework, because of these primitives that it comes bundled in. But if you don't want to go through all that, building things from the scratch, having to implement your own human in the loop support and checkpointers and stuff like that, you can use pre-built components. Yeah, you can use pre-built components. So LangGraph provides pre-built components that you can use to build things like React agent. I need to build React agents. So you can just use those components, and they come with a lot of these capabilities out of the box. You don't need to implement them manually. So based on the level of control you're going for, how granular it is, you can either use the primitives, which you have the Graph API and the Functional API to work with, or you can use a bunch of the pre-built components that come out of the box. We're going to be playing around with the two of them. We're going to be spending a lot of time with the primitives, because I want to teach you how to build everything from scratch. And we're also going to be using the pre-builts. And with your knowledge of the primitives, you can know the benefits of the pre-built, and you can also learn more or understand how you can customize them to what you want. So in a previous video, I mentioned that there are two ways to create agents in LangGraph. You can go with primitives. That's if you want to build your agents from scratch. You want to build every single thing about your agents from scratch. And you can also go with LangGraph's pre-built components for creating AI agents. One of the primitive ways for building AI agents in LangGraph is called the Graph API. And that's where LangGraph got its name, as you may have guessed. That's where LangGraph got its name. the Graph API. Now there's the functional API, which is kind of new as at the time of recording this video. The functional API is kind of new, but the Graph API is what started LangGraph, and it's still what a lot of people use when they are using LangGraph, and it's still the most popular way of using LangGraph. And what this does is that it represents your agent interactions, the decision making, the action taking as a graph. It represents it as a graph. So basically, that's how the Graph API works. And if you look at it closely, as we'll be seeing in this video and a lot of videos to come, it's basically like a state machine. It's basically like a state machine. So you have state being maintained, and across different nodes, state gets to change based on different actions going on. But enough talk. Let us get into the whiteboard and see what the Graph API is all about. Let's see how the Graph API works. So yeah, LangGraph Graph API. Like I said, the Graph API basically represents the agent workflows and interactions as a graph. And it consists of three main parts. So it consists of state, nodes, and edges. State, nodes, and edges. Those are the three main parts of the Graph API. Those are the three main components of the Graph API. Now let us look at this one by one. Now, your state, and I'm just going to represent that with this. Let's come here. So let's say this is your state. Your state is the overall data structure that is being maintained across the agent interactions. Is the information that the agent is working with, the information that the agent needs to hold in order to perform its operations. That is what is contained in the state. And the state contains every single variable or state variables representing those pieces of information. Let's say, for example, we use our email example from one of the previous videos. Let me just put it down here. So let's say we want to have an agent that just helps us create and send emails. So for the state, we can say, okay, inside the state, we want it to have sender. We want it to also have recipient. So we want to have sender, recipient. We also want it to have the body of the email. Then we also want it to have a status property. So these are data that are important to the operation of the AI agent. These are pieces of data that are important to the operation of an AI agent that wants to help us build and send an email. Now you can keep adding more based on the needs of your AI agent, but let's say this is what we're working with. So this is the state. And typically you represent your state using a dictionary. You represent your state using a dictionary, even though you can use any data type, but just use a dictionary. It's easy to bundle different types of information inside the dictionary. So that's your state, the operational data that your agent needs to work with in order to perform its task. That's the state. Then we have nodes. So I'm just going to get some circles here. We have nodes. I might be wondering why I'm drawing circles, but don't worry, you will know very soon. Now, what are nodes? Nodes are basically the action takers in your AI agent. Yeah, nodes are the action takers in your AI agent. So any action you want to take, any operation you want to perform, be it calling an LLM, typical code operations, drafting an email, doing a check, validating and stuff, any piece of action you want to perform is performed in a node. So nodes are the action takers inside your AI agent. And typically, nodes are functions. Those are Python functions. Like if we're going by Python, if we're talking in terms of the Python SDK, because there's definitely a JavaScript SDK also. So they are basically functions. They are functions. If it's the JavaScript SDK, they are also JavaScript functions. If it's Python SDK, they are Python functions. So they are just normal, pure Python functions. No need to overthink them. And they are action takers. Now, that's node, and you can use them to perform any type of action. Any type of action that your agent needs to take. And also think of them as like the steps in your agent's operations. The steps in your agent's operations. Be it fixed steps or conditional steps, they are they represent the steps in your agent's operation. Now, each node function, let me have some text here so I can describe that. Each node function, let's say def node A, will take as its argument the state of the AI agent. It will take as its argument the state of the AI agent. That's something to note. So every node can take the state of the AI agent and can access it for information that it needs or to perform some of its operations. So that is one thing with nodes. Every single node takes by default the state of the AI agent. They can also take other things that we're going to see later, for example, the runtime context. But looking at AI agents as state, nodes, and edges, every single node in a LangGraph AI agent takes the state. It takes the state and it can access the state for data and also use that data to perform operations. So that is nodes. That's what nodes typically do. And aside taking the state of the AI agent, they also return the update to the state. They can also return updates to the state. They are basically the components that will be mutating the state of the AI agent. They are the ones that will be changing the state of the AI agent. So for example, let's say we've finished sending our email and it is successful. In this example, the status variable in the state is going to be changed to success or true, whichever way you want to label the success indicator. You can either call it success as a string or true boolean. So nodes typically return the update or an update to the state when they are done operating. So that's node. Now let us look at edges. What are edges? Now edges typically determine how the flow of the AI agent is going to go. Yeah, they determine how the flow of the AI agent is going to go for the particular operation it's supposed to perform. They are your connectors. So they say, yeah, after you're done with this node, then go to this node. Then once you're done with this node, go to this node. And once this node is done operating, then go to this node. Yeah, those are your edges. That is what edges do. They basically connect nodes. And later on, we will see that this connection can be conditional. It can be conditional because some operations you want to perform are conditional. But just looking at it in a simple form, they connect nodes. So they determine the flow of operations. That's what edges do. They determine the flow of operations. And there's no orphan node. There's a node that is connected to an edge either by a fixed edge or a conditional edge. You can have an orphan node. Now for fixed edges, you basically just connect them from one node to another. You could typically just connect them from one node to another. That is for fixed edges. But for conditional edges, you can define them as functions. And when you define the edge as a function, it can also take in the state. Your edge can also take in the state of the AI agent. It can also take the state of the AI agent because most likely it needs some sort of state information to be able to take a condition. Yeah, it needs some sort of state information to be able to take a condition. For example, let's say we want to, we have two nodes, one that drafts emails and one that sends emails. It will be good to check if the email has been drafted before we go to the node that sends it, because you don't want to send an email that contains an empty body, that doesn't contain a body. So you can have a condition that checks, okay, is the body property in the state, is it not null? Is it not empty? If it's not empty, then you can direct yourself to the node that sends the email. If not, you go to the node that drafts the email. So that is one of the things you can do conditionally with edges. So just to recap, just like nodes, if edges need to perform conditional operations, you can define them as functions, and they're going to determine the next place that you're going to go from a particular node. They're going to determine whether to go to node A or node B based on a condition. So those are edges. And just like nodes also, they can also use LLMs. They can use LLMs. If you want the decision making to be dynamic, yeah, you can always delegate that to an LLM, and the LLM is going to help you to dynamically or rather use its intelligence to determine the next node to go to. So, but basically, it's pure Python functions, the same type of operations you can perform in your typical Python functions. That's what you can perform in node functions, and also when you need to define your edges as functions. So, to wrap up our whiteboard session, typically, how do you build a graph in LangGraph? How do you build a graph in LangGraph? Now, the first thing you're going to do, let me get out of this green text. Yeah, the first thing you're going to do is to define your state. That's the very first thing you do. You define your state. So you define your state variables, you use a dictionary. There's a state graph class. So you use the state graph class. The state graph class, but don't worry, we're going to see it in the demo. The state graph class that you need to define your state. No, I'm not trying to expand that. I'm trying to move it. Yeah, so there's a state graph class that we're going to be looking at that you use to define your state. Now, once you have your state defined, the next thing you're going to do is to create your nodes. To create your nodes, that is all the steps that you need in your AI agent. You create them as nodes, and those are basically Python functions that can receive the state of the AI agent. And once you have your nodes created, you connect them with edges. You connect your nodes with edges. Connect your nodes with edges, and once you have all of them connected, you have your graph. But before you run your graph, you need to compile it. Yeah, there's a compile step to your graph. So you need to compile your graph. You need to compile your graph, and once you have your graph compiled, you can then run your graph. Yeah, run your graph. Can I run your graph? So these are the steps that you need to create your graph, and we're going to be doing that in the demo that is coming right up. Now, before we go there, I would like to point out that there are two standard nodes in LangGraph. There are two standard nodes that come out of the box with LangGraph, and these nodes are the start and end nodes. The start node and the end node. Now, LangGraph provides this node for you to be able to define the starting point for your graph and also where your graph is to terminate. Yeah, the starting point for your graph and where your graph is to terminate. That is why these nodes are essential. But we're going to be seeing them in action very soon. So let's jump into Visual Studio Code and build our very first graph. So here in VS Code, let us build our very first LangGraph graph using the Graph API. Definitely. The first step we're going to take is to create a new virtual environment, a new Python virtual environment. So I'm going to do Command Shift P to just use VS Code to create that. So create a new Python environment, create a new Python virtual environment. That's good. Now the demo that we're going to be building, the graph that we're going to be building, is just going to be a simple graph that will take will hold a list of messages in the state. It will hold a list of messages in the state. And we're also going to be using one of LangGraph's built-in functions to update the message list. Don't try to cram a lot of things you're saying in this video. This is just a demo for you to see how graphs work. In the subsequent videos, we're going to be breaking all these things apart, nodes, edges, and having individual videos, even multiple videos that get to treat these topics. So, but for now, enjoy the flow and just try and understand how a graph is built. So once we have this in place, we can then create our file. Create a file. I'm just going to call it graph api.py. Graph api.py. So this is where we're going to be building our graph. Now, before we can build our graph, we need to install LangGraph. We need to install LangGraph in this project. So I'm just going to quickly do pip install LangGraph. And that's how you install LangGraph to your project. Yeah, just the LangGraph package. And it also comes with LangChain as a dependency. So sometimes when we are importing from LangChain packages, it already comes with LangChain, so you don't need to install that separately. So we're going to install this, and that shouldn't take long. But if it takes long, definitely I'm just going to pause the video and we're going to come. So the installation is done. Let us clear our terminal. And for now, just close out of it. We don't need it right now. Oh no, I'm not closing. Yeah, doing it right now. Now, let us start creating our graph. Now, to begin, first I'm going to be importing 3 important components from LangGraph. So I'm going to say from LangGraph, from the graph model, we're going to import 3 things. And that will be state graph, which, like I said, is a class that we use to create our state. Then we're going to also be importing the start node, that standard node I told you about. And we're also going to be importing the end node. So those are the 3 components we're going to be importing from the graph module of LangGraph. So say state graph, then start and end. So that's good. Now, to do some type hinting, I'm going to be importing some, say from typing, import annotated. Also going to import list and also import typed dict. Typed dict. We're going to be using typed dict as our dictionary, for our dictionary to define our state schema. But like I said, there's a whole state video for you to understand all that coming soon. But this is just for us to do some type hinting on the properties that we have in our state. Now, the last thing I'm going to be importing is going to be that special function from LangGraph that I said can help us manage a list of messages. It's basically designed to manage a list of LLM messages. Like I said, more on it later or in later videos. So I'm going to say langgraph.graph.message, and from there we import add message. It's actually called a reducer. It's called a reducer. Add message or add messages? Add messages. Yeah, that's why I didn't turn green. So this is actually called a reducer, and a reducer is basically a function that helps you mutate your state, or rather update your state. So, but like I said, in dedicated videos, you're going to be learning about all this. So yeah, we have the add messages function, or the standard name reducer, and now we can start to create our AI agent. Now, the first thing I said is that there are certain steps we'll take to create our graph. So in order to follow this example easily, I'm going to list out those steps. So like the first thing we're going to do is to define our state. So the first thing we do is define our state. Then we're going to create our node. Then once we create our nodes, we link our nodes with our edges. And after that, we're going to compile our graph. And then we can run our graph. Yeah, those are the 5 steps we're going to be taking to create our graph and run it. So let's start with step 1. So in step 1, we're going to create our state schema, which is going to be a class. We're just going to call it simple state. And simple state is going to inherit typed dict. And inside we have a messages property that we will annotate and say it contains a list of messages, and it is managed using the add messages reducer. So we have our state, and in order to create our graph, I can just say graph equals state graph state graph, and we instantiate it with our simple state. Yeah. So everything starts from our graph. And what our graph needs is our state schema. So giving it our state schema, so we have a graph now. But our graph is empty. It doesn't have nodes and it doesn't have edges. So let us do that next. So we're going to be creating 2 nodes. One node is going to add the word hello into the list of messages, while the other node, as you may have guessed it, is going to add the word world to the list of messages. So this is basically our hello world project to LangGraph graphs. So like I said, nodes are basically Python functions. They are pure Python functions, and they receive the state of the graph. So let us create our first node. I'm going to call it say hello. And like I said, it receives the state, which is an instance of simple state. And here we can just print and say executing say hello. Just tell us the node that is in operation. Say hello node. So executing say hello node. And what we want to do here is just update the state. Update the state by adding the word hello into the messages list. And to do that, you simply return a dictionary containing the parts of the state that you want to update. Not all the parts. The parts that you're not going to update, you don't need to return them. Just return the parts that you want to update. So we want to update the messages state variable. And inside it, we want to put the word hello. Now, because messages is a list, we always have to represent it as a list. So we're putting the word hello, but we have to put it inside the list. And we can tack on more items to this list. But for now, the word hello is good. So by returning this dictionary, we are telling LangGraph, update this state variable with this value. Now, because we're using the add messages reducer, or the function that is going to be helping us update the state variable, it will append anything we return. It will append it to the list. But later on, we're going to see how reducers work by default, or in the reducers video. But for now, what it will just do is to append whatever we send back to the state into the messages list. So yeah, we have this for say hello. I'm just going to create the second node. And this one will be called say world. So yeah, executing say world, and it will add the word world. To add the word world to our, so in this in place, we have our two node functions. Not the node yet, the node functions. We still have to convert them to nodes. So how do we make them nodes? To make them nodes, we come down here, we call on the graph, and on the graph we call the add node function. Now the add node function is going to take two arguments. First is the name that we want to call this node. Yeah, the name we want to call this node within our graph. And I just want to call this the hello node. Then the next function is going to be the next argument is going to be the function I want to run, the function that this node runs. And that will be the say hello function. So yeah, that's how we add our node. So we can just copy this and add our second node. Our second node, we'll call it the world node. And it will run the say world function. Awesome. So that's cool. We've added our two nodes. Now we have them in place. Now the next step is to link our nodes with edges. So we want to define the flow of the application. So how do we want this graph application to operate? Definitely we want to start. Let me make this a comment. So we want to start, and once the graph starts, we want to say hello first. So we'll go to the hello node. Once the hello node is done, we want to say world. So we move to the world node. And once the world node is done, we want to terminate. Once we just terminate our graph, so we'll go to the end node. So that's how we want to operate. So just keep that in mind. Now, the way you add edges in LangGraph is by calling the add edge function of the graph. Called the add edge function, and you can add from one node to another. Later on, we'll see how you can add conditionally to two nodes, or decide which one to go between two nodes. But for now, we just go from one node to another. So the first thing we want to do is graph dot add edge, and we want to go from our start node, that's our entry point node, all the way to our LO node. Let's go to our LO node. Now, here you have to use the names you give your node, not the function names. You can make them the same, and sometimes you can even just pass the function to add node, and it will just assume that the name of the function is also the name of the node. But we're being explicit here, and so that you can see how everything works, so that you can see how everything is constructed. And here you have to use the exact name of your. So here we've defined the first step. Now let's go to the second step. Now here what we want to do is to go from LO node to world node. We want to go from LO node to world node. So just going to put in quotes, say LO node, close out of this. And from LO node, we want to go to world node. From LO node to world node. So that's the next step. First we went from start to LO node. Then now we're going from LO node to world node. And yeah, definitely for the last step, we'll go from world node to the end node. Yeah, to the standard end node. So let's say add edge. Now let's go from world node and end things there. Yeah, terminate our graph. So we terminate our graph here. So that's good. That's all cool and smooth. Our next step is then to compile our graph. We need to compile our graph. And to do that, all we need to do is say agent. Let's say that's our AI agent variable. Agent equals graph.compile. Graph.compile. This is a very important step. This is how you get your application. This is how you get your agent application. You compile your graph, then you have your agent application. So we compile, and now we're good to go, and we can run this agent application. To run it, first let us define what will be the initial state of the state. Yeah, what will be the initial value of the state? So I was going to say initial states, and for the messages, because that's the only variable we have in state, so we'll just say messages. And for now, messages can just be an empty list. So messages is an empty list to start with. You can initialize with some values in here, but we're just starting clean. So initial state, and now we can get a final state by running our graph, which we have called agent. And what we get back when we compile, this is something to note. When you compile your graph, you get back a runnable. Yeah, you get back a LangChain runnable. So you can call your typical invoke, batch, and stream functions on it. So we get our agent, and we can invoke it with our initial state. You can invoke with our initial state. So we just pass in the initial state. And then we can print out our final state. So I'm just going to come here and say print. Final state. And for now, we'll just print it out raw. So print final state. Print final state. Awesome. So yeah, now we followed all our steps. We first defined our state. We defined the state schema using a typed dictionary. We created our graph by calling state graph, passing in our state definition. Then we created our nodes, two nodes, say hello and say world. And we also made sure that we created them as nodes so that the graph can identify them. Then we link our nodes with edges following the flow that we want it to go with. And once we have that, once we have our nodes connected with edges, we compile our graph, giving us back our agent. And now we can give our agent an initial state. I added an extra S. So messages, we create an initial state and we pass it into the invoke function of our returned graph. Because what we get back after compiling is a runnable. So you can do all typical runnable stuff. It has all typical runnable properties. And later on, we're going to see that we can actually configure it like a runnable also. Then we print out our final state. So that's all good. Now it's time for where the rubber meets the road. Let me pull up the command line. Okay. Yeah, that needs to go down. Pull up the command line. And now let us run Python graph API.py. Python graph API.py. Let's hope that we got everything right. And here we can see the output executing say hello node, executing say world node. And at the end of the day, we get this final state where we have our messages, which is a list, and it contains two human messages. If you look at the content of the first one, it says hello. The content of the second one says world, and those are the messages contained here. Now, you might be wondering, why is it looking weird, human message and all that? That's because we used add messages, which is actually built to work with LLMs. So we use add messages to add messages to our messages list. So that's why you're having this LangChain structured message object inside the list. If you use typical strings and we use a custom reducer, definitely you will see that we can just have simple strings inside our list. But because we use add messages, which is built for working with LLMs, we have those message objects, human message objects. So yeah, that's our graph. And before we wrap up this video, I'm going to throw in a bonus, and that is the fact that we can actually visualize our graph. Later on, we'll also see how to use a tool like LangGraph Studio, which is a more specialized tool for visualizing graphs. But you can also visualize your graphs within your command line. You can even generate like PNGs of it using Marmite. So to do that, let's clear this first. Now, for you to visualize your graph, you need GrandAlf. You need GrandAlf package. So first, we need to install that by saying pip install GrandAlf. Install GrandAlf, and let's just wait for that to be done, and it's done immediately. So now we can get to work. Let me close this for now. Keep pressing this button. Okay, for this I'm going to comment out where I'm actually running the graph. So we'll just do that like this. So for us to get a visualization of the graph, we'll say print. We'll take our agent, we'll call the getGraph method. And on the getGraph method, we will tell it to draw the ASCII representation so that it can display well on standard output. Yeah, and that's basically it. Let us see how it looks. Pull up our command line once again. Going to run a file, and boom, we have our graph representation. As you can see, it starts from the start node, then it goes to the hello node. And then from the hello node, it goes to the world node. You can see the nodes are represented as rectangles, and the edges are represented as dotted lines. So it goes to the world node, then goes to the end node. Amazing. So we have already looked at how agents work in LangGraph, and we've also looked at what the Graph API consists of. The Graph API is one of the primitive ways you can build agents from scratch in LangGraph instead of using pre-built components. Now, the very first item, we said a LangGraph agent consists of three parts: that's state, edges, and nodes. And in this video, we're going to be looking at the very first part, the state. Now, the state is the very first thing that you define when you are defining your LangGraph agent. The state is the very first thing you define, and at the end of the day, your graph is basically just a state engine. So as state passes through each node, it is updated, and at the final point, you have a final state. So let us look at state. Let us get to our whiteboard so that we can have a better understanding of what state is in LangGraph agents. So let's say we have our graph. Let me give this a background. Let's give it a background. Let's give it a mesh background. So let's say this is our graph. Now, your state is the pieces of data that you need to hold through the session of the agent's operation. Yeah, the pieces of data that you require for the agent to perform its operation. Now, this is not data that is fetched from a persistent source. No, for the duration of the operation of the agent, these are the pieces of data that you need to control its operations. So let's say we have our agent, and the first thing we do is define our state. So we define a state. Let me make this, let's make this solid. So we define our state, and let's say our agent is meant to, let's assume, recommend a bunch of students in a class to be qualified for a field trip. Recommend a bunch of students to be qualified for a field trip. So we can say inside our state, let me get a checkbox for that, or a text box for that. We can say inside our state, we need the total number of students. So I say total num students. We need the total number of students in our state. Let's make this wider. Make this wider too. You know what? Let's just make everything. Let's just increase everything. So I'm going to increase this. I'm also going to increase the box inside. Good. So we need the total number of students in the class. And let's say we want to make them qualify for the field trip based on an average score. So let's say we want to have that average score. Probably they have to take a test. So based on the average score, we need to select students that will be qualified for the field trip. Then we also need to also hold the number of students that are qualifying for, they are going to qualify for the field trip. So let's say qualified students. This is the total number of students that we selected. On and on and on. You can always model your data based on what you require in your state. So we need the total number of students. So we need to count the number of students and just put it in state. We need the average score that will be required. And if this changes, we also want to be able to update it. And we also need a list to hold our qualified students. Let's just say these are the items that we need. Now, this is the state. This is the state of the application. And throughout the operation of the agent, this is what is going to be updated. You can provide initial values for some of them. For example, total number of students, something that can get an initial value. Average score can get an initial value. But while the agent is operating, you'll be selecting students and be filling them into the qualified students list. So this is your state. This is your state. Now, state consists of two things. State in a LangGraph agent consists of two main things: the schema and the reducer. So we have schema. State consists of schema and reducers. Schema and reducers. Probably is more appropriate here. So schema and reducers. That's what a state consists of in a LangGraph agent. Now, what is a schema and what is a reducer? What we just defined, the data model that we just defined with our num students, average score, and qualified students, that's our schema. That's our schema. Your data definition, your data model is your schema. That's the schema for your state. Now, what are reducers? Reducers determine how your state is going to be updated. Yeah, the main function of reducers is to apply updates to your state variables. These are state variables. Total num student is a state variable. Average score is a state variable. Qualified student is a state variable. And they are all keys inside your state schema. So reducers control how these state variables are going to be updated. And each state variable has its own reducer. Each state variable has its own reducer. There's another video coming up on reducers, so we'll get into that more. For this video, or rather in this video, we're just going to be defining schemas. But like I mentioned, there is a reducer for each state variable. So total num student has its own reducer that determines how it is updated. Average score has its own, and qualified student will also have its own. Now, if you don't apply any reducer to any of these schema variables, there's a default reducer that takes charge. But like I said, there's a whole video on reducers where we're going to be treating that. But for now, let us head into our code editor and see how we can define our state schema. So here in VS Code, we are going to be playing around with different ways we can create our state schema. The state schema for a LangGraph agent. Now, LangGraph provides different ways for you to create a state schema. You can use a plain dictionary. Like I said, LangGraph agent state is mostly represented as a dictionary. So you can use a plain dictionary, a plain Python dictionary. You can also use a typed dictionary from the typing class. So you can do that also. And you can use a data class. Data class gives you the ability to set default values. And also, if you want to go full-fledged, you can use something like a pedantic model. You can use a pedantic model, which is very, very awesome and allows you a lot of granular configuration for how your state variables are defined. So in this demo, we're going to be working with a simple dictionary. We're also going to be using a type dictionary, and we're also going to be using a pedantic class to create our agent schema so that we can see how this operates. We can see these options, and you can choose anyone that is appropriate for your use case. Now, to get us started off, we have a piece of code here that already defines a graph runner. Let's just walk through it. So we import the typical things from LangGraph. So we have state graph to instantiate our state. We have start and the standard start and end nodes. So we have that. Then we have two nodes. We are defining two nodes. Rephrase. Then we have a couple of nodes, two of them that are going to be in this example. We have node A and node B. But before I talk about the nodes, this is how our state is going to look like. Let me just get us clear on that. Now, this state object is not going to be for any particular application. We're just going to be dumping a bunch of stuff inside and see how we can update them. So we have a messages list, which is just a string list. We're going to have a step count state variable, which is basically an incrementing integer value, or it's meant to increment, but it's an integer value. And we have private data. We are going to have a private data variable also, which is just a string that we can dump anything into. So these are going to be our state variables. But like I said, when you're defining your state, it would represent the data structure that your graph needs to operate. So we have this. Then we have two nodes. And we've named them node A and node B. Now, what does node A do? Node A takes the state. Like I said, every node takes in the state by default. So it takes in the state and it updates the messages list by adding this entry, which is step A completed, and also a step count, which is more like a step counter for the nodes that you hop through. So it also updates the step count by 1. So, then we have node B. What node B does is that it also updates these two items. But like I said, we can use a plain dictionary. So if you want to access a plain dictionary, it's different from when you want to access your schema if it is built with something like a type dictionary or a pedantic model. So we have to put this check so that we can access one of our state variables and just print it out. This is just for us to print out a state variable, just to show that you can access a state variable inside your node. But the main thing we're doing here is that we're also updating our the two state variables I want to update, that's messages and step count. We're not updating private data, just to show you that if you don't perform any update, you just have your state that way. And like I said in our Graph API video, you only need to return the state you want to update. So you don't need to return the entire state. For example, like I've described above, this state has a private data state variable, but we're not updating it in any of the nodes. So we're just returning messages and step count, which are the ones that we're interested in updating. Then we have this function, which is just a convenient function for us to run our graph with different schemas. We don't want to have to build the graph for every single example that we're going to be doing. So I wrote this function. What it basically does is that it prints the schema that we're working with. It prints the name of the schema. And also, if it's a dictionary, it does that check, because working with plain dictionaries is just kind of an outlier. It's like the dark horse of all these examples. So it just prints, dictionary. But if we're using any of the other styles, it prints out the name of the state schema type that we're working with. Then we use our state graph to initialize our state, as you have seen in our Graph API video. So we initialize our graph with our state graph using then we had our two nodes, node A and node B. We had our edges. First, we start with our start node connected to node A. So from start, we go to node A. Then from node A, we go to node B. And from node B, we go to the end of our graph. We terminate our graph. So we compile the graph. We invoke it with an initial state, which is passed into this function, build and run graph. So we pass in our initial state. So we use it to run our agent or our graph. and print out our final state. So that's basically what this function does. Is nothing new. It's just similar to how we build graphs. It's just to make sure that we're not writing this entire code over and over for our different examples. Now let us start with our examples of creating a schema in LangGraph. So I'm just going to collapse all these functions so that we can have some room. I think I need to come down out of this function. My scroll bar is very, very fast. Okay, so come out of this and go up and collapse this. Now to our very first example. Our very first example will be using a plain dictionary. Using a plain dictionary. Now for that, I'm just going to simply define a function called create dictionary state or create dict state. And what it's basically going to do is that it's going to return our state, just to return an initial value for our state. So say messages. That will be an empty list. Then we have step count. I'll set step count to 0, which shows the initial point of our node hopping. Then private data is going to be set to none. Just set that to none. So we've created this, and then we can just take our function, the build and run graph function. I hope I'm spelling it correctly. Build and run graph. Yeah, build and run graph. So our build and run graph function. First, we tell it what state schema we're working with. What state schema we're working with. We're working with a dictionary. So we give it the standard Python primitive dictionary. So we're working with that data type. And what's our initial state? What's our initial state? For that, I'm just going to give you this function so that it gets our initial state from this function. So we'll do this. We'll call the function. And now I'm going to pull up my command line. Let's clear this up. And now let us run this file. Python agent state.py. Let's run it. So here we're getting an error. And the error says that there's no module named LangGraph. Now that's just a silly mistake by me. I'm not in my virtual environment. So let us make sure that we're in the virtual environment before doing that. So I'm just going to activate it by saying source vmv.venv rather bin activate. So now we're in our virtual environment. That's good. And we can run this file once again. Python agent state. And boom. Yeah. Building and running graph with state schema dict. So we got the right data type that we're using, the dictionary. It says executing node A, executing node B. Current step count from state is 1. And the final state is this. Step B completed, step count 1. So our step count is no longer 0, it's now 1. And our messages list says step B completed instead of just giving us an empty message. So we've been able to update our state through node A and node B. In node A, we set the step count to 1. And for the messages, we say step A completed, step count 1. Then for node B, we say step B completed, which is what we got in our final state. And the step count is also 1. Now you might be wondering, why don't we have step A completed and step B completed in our message list? And why is our step count not 2? Because we actually hopped through 2 nodes. Now that's because we're currently using the default reducer, and the default reducer is going to simply override the data in a particular state variable. It's just going to override the entire data. So even step A made step count to be 1. It returned 1. So step count to be 1. And step B also returned 1. So step count will just be 1. There's no increment. There's no incrementing. For us to increment, we need to define a custom reducer. But let's go on. For now, we are here for state schemas. So let's just focus on that. And now we've been able to see the dictionary example. The next example we're going to look at is the typed dictionary example. That's a typed dict example. Creating a state schema using typed dict. For typed dict, to make things fun, I'm going to be adding some custom reducers. So the first thing we're going to do is to import some helpers that we need, which includes typedict itself. So I'm going to say from typing, give me annotated, give me list, and also give me typedict. So we have those 3 items that we're going to be using to create our schema. I'll also be needing the help of a useful LangGraph function called add messages. We're going to be talking more about add messages in another video, but it's basically a built-in reducer that LangGraph provides for you to manage LLM messages. So you can use it to manage a list of LLM messages. Basically, the most important use case of it is chat history. So you can use it to maintain your chat history. So I'm going to be bringing this in to define my schema using typedict. Now for the typedict schema, let's go down. Let's create a new section for a new example. We'll say using typedict. Now to create your schema using typedict, the first thing you need to do is create a class for your schema. I'm going to call it typedict state. And this is going to inherit the typedict class. Because you inherit that class, and here you can just go on defining your class members. And those are going to be your state variables. So first, let us start with messages. And one of the, or rather the main advantage of using type dictionary is that you can now use type ints. With a plain dictionary, you can use type ints, but if you define your state using type dictionary, you can use type ints. You can't set default values though, but you can use type ints. And typedict works seamlessly with LangGraph, so it's one of the recommended ways for you to create your state schemas. So for messages, we're going to annotate that variable. It's going to be a list of strings, and it is going to be managed using the add messages reducer. We also do step count. Now step count is going to be an integer still, but then we want to be able to update it to actually increment. We want to update it to increment. So what I'm going to do is that I'm going to create a custom reducer for this that's going to help us increment the value. So just above here, I'm just going to define, say, custom add. And reducers, basically, if you're going to define them yourself, they take in the current value of the state variable and the new value that is coming in. That's the new value that is being returned by a node. Those are the two things that they take. So for this, I'm going to say current. I expect it to be an integer. And new, which I also expect to be an integer. And definitely I want to return an integer, so that should kind of be implied. Now here I'm just going to return the summation of the two. That's just add the current to the new. So if the step count is currently 0 and we return 1, it's going to add it to 0, and that will be 1. If the step count is currently 1, if we add another 1, it's going to be 2. So we're just going to put this here. That's going to be our reducer. And yeah, you're seeing how to add reducers from this video, but like I said, we have a whole video on reducers that we are also going to use to drill down on these things. So step count, and finally we have private data, which we're still not interested in, so I'm just going to set it to a string for now. So now we have our state schema created with a type dictionary, and now we can use this example to build our graph and run it. So I'm going to say build. I'm just going to copy that. Build and run graph. Build and run graph. Now to run this, first we need to pass it our state. So we'll say typedict state. Pass our state schema, and then we pass it an initial state. What's the initial state, which you can simply pass using a dictionary. So here we're going to say messages. For messages, we start with an empty list. Then next we have step count. Step count is going to be 0 to start with. Then we can do private data. And private data, we're just going to set it to an empty string. Set that to an empty string. So message is an empty list, step count 0, and private data is an empty string. So let's pull up our command line and let us run this file once again. Say Python agent state.py. Let's run this. And now we are executing A and B. Yeah, we get it. But these are our final states. These are our final states. And if you look at this, messages, we have a human message. We have a human message here. And when we check the content, we'll see step A completed. If you look into the list, you see another human message. And this content says step B completed. So, and now instead of having the messages list overridden by the most recent value, we now have both values inside for step A and for step B. And you might also wonder why we're having human message, why we're having why we're not just having a list of pure strings that just says step A completed and step B completed. And that's because we're using add messages as our reducer, and add messages is basically built for LLMs to update a message list. So that is why it is adding human messages from the LangChain messages class. So that's why we have that. That's why you're seeing this weirdness. But you can still use something like operator to just add your string input, and it will just add it as strings if that's what you want. If we look at step count this time, step count is now just 2. Step count is 2. It's not 1. That's because it is incrementing it. True node A incremented it by 1, so we had step count as 1, and true node B it incremented it by 1 again, and we have step count as 2. And private data stays empty. So yeah, that's working fine. Our LangGraph reducer is doing its thing. Our custom add reducer is also helping us manage our step count. So that's cool. Now let us go to our final example, which is using Pydantic. We're going to be using Pydantic, which is a very awesome library that you can use to define your schema, and it gives you validation, it gives you type ins, you can set default values and stuff like that. So we're going to be making use of that next. First, I'm going to clear the command line. Let's close out from this. I'm going to comment out this step. And we're going to create our third example, which is using Pydantic. Now to use Pydantic, first we need to bring in the library. Say from Pydantic, let us import base model, which our schema class is going to inherit from. And we're also going to import field, which is the exact class that's going to help us build up our state variables. Any extra information that we want to add to our state variables, field is going to help us do that. So we have those. I'm also going to be bringing base message from LangChain core messages. Going to be importing base message because for our messages list, since we're going to be using add messages, we want to make sure that we are defining it with base message in Pydantic, because Pydantic has validation, and if we call it a list of strings and we are trying to add a message type from LangChain, it's going to throw an error. So we have base message, and now we can go down and use Pydantic to create our schema. So first we're going to create a class, and I'm going to call this Pydantic state. This is going to inherit from the base model class. Going to inherit from base model class, and then we can define our schema. We'll start with messages, set that to an annotated type. It's going to be a list of base message. It's going to be a list of base message, and we're going to be managing it using the add messages reducer. So this is good, but we're using Pydantic, so we can do more. For the field, I'm going to set this as a default factory, and the default factory we call list. Now, why are we doing this? We want to make sure that every instance of this state class rather gets a new list. Else, Pydantic is going to share the list between as many instances as you create. We don't want that. We want every instance of this state to come with a fresh list. So that is why we're doing this. So we have that in place. Then for our step count, we're also going to define it similar to what we did with the type dictionary, custom add. But with Pydantic, we can use field to set a default. The default equals 0. So the default. And lastly, for private data, which we have been ignoring, within our nodes, we're just going to set it as we set it as string, and we also add a default value to that. So we set it by default to an empty string. So now we've defined our state schema using Pydantic. We have a Pydantic state now. Now let us build and run it. Let us run it through our graph. So once again, we're going to come here and say build and run graph. Our state is Pydantic state, so we're going to give it that. And for our initial value, we just instantiate a new Pydantic state. So just we create a new instance of Pydantic state, and what it's going to do is just going to take all these defaults. So we've already set default, so it just takes the default. Step count is going to be 0. Private data is going to be an empty string, and we're going to get a fresh list for our messages list. So let's save this. Now let us run our code from the command line. Once again, and say Python agent state.py, and boom, yeah, our code runs. Node A is executed, node B is executed, and for our final state, we have our list of messages once again, with step A and step B completed. Our step count is 2, and our private data remains empty because in our node we're not touching our private data. So in this demo, we have been able to use a plain dictionary. Use a plain dictionary for our state schema, the Python primitive dictionary data type. Then also we use a type dictionary, and we started adding reducers so that we can actually see how state is updated. And we finally used a Pydantic model, a Pydantic based model, to define the schema for our agent. So these are options you can use. Data class is also an option, so if that works for you, you can also use that. Data class and type dictionary works. They are faster, they are more efficient than Pydantic, but Pydantic gives you more options. So and most of the time, I don't think the performance hits that you get from Pydantic are going to be really severe. But if it starts piling up, then you know where that optimization task can come from. Type dict and data class, they are more performant than Pydantic, but Pydantic gives you more options. So that's how you define your state schema in a LangGraph graph. So in this video, we're going to be discussing state reducers in LangGraph. We're going to be discussing it, and we're also going to be looking at some demos in code. Now, if you watched the state schema video or the Graph API introduction video, you definitely have heard something about, I heard me mention reducers. If you have not, go watch those videos. Now, if you've heard me talk about reducers. Now, state variables are variables. So that means they're not static, they can change. So we need something to update them. And nodes help us update state variables. State variables are updated through our nodes. But you can define, or something manages how they are updated. Something is responsible for how these state variables are updated, and that's the reducer. The function of the reducer is to determine how a state variable is updated, so that when a node returns a new update for the state variable, the reducer is then called upon to manage that update. But to understand better how things work, let us head into our whiteboard. So let's say we have our states. Let's say we have a bunch of states here. Let us just use from our previous example, let's say messages. So messages is a list. Messages is a list. It's an empty list. Then we also have step count, We have step count. Step count is an integer and it starts from 0. Then we have private data. Private data is just a string. It's just a string. Private data is a string. And it's empty. Yeah, it's an empty string. So we have these state variables. We have these variables in our state. Now, these don't represent anything, so don't try and figure out what this what these all mean or what's related with. These don't represent anything. We just need a bunch of variables to work with. So we have these 3 variables. And through each node, they need to change. So from one node to another, from one node A to another node B, this need to change. They need to change. And you can choose to change one of them, multiple of them, or all of them. Now, how they change is the responsibility of the reducer. Yeah, the reducer takes care of how they change. Now, the thing with LangGraph is that if you don't define any reducer, there's a default reducer already in effect. Yeah, there's a default reducer already in effect. Now, what this default reducer does is that whenever you return a new value for a particular state variable, the existing value will be overridden by the new value. The new value is going to override the existing value. So let's say for messages, we bring in a new value. Let's say we have a new array. Sorry, I keep calling it array a lot because of my JavaScript background. A new list. So let's say we come with a new list, and the list says step 1. Set as a new list, say step 1, and is the update for this particular variable. This entire list is going to be replaced with this value. The entire list is going to be replaced with this value. So it then becomes, this then becomes step 1. Becomes step 1. Now, if another node, let's say node B, updates this variable once again, and let's say it says step 32, you are not going to have step 32 added to this list. No, you're not going to have it like this. You won't. This new value, step 32, is going to come here and override the existing list. It's going to override this entire list. It's going to override it. It's going to override this entire list. And the same goes for step count also. If you have a new value for step count, let's say you have a value 5 for step count, and that is returned by a node as the update to step count. Step count automatically is going to be changed to 5. It's going to be changed to 5. Even though going by the name step count, you kind of want to increment it. Sometimes you want to replace it. Probably that's what you want to do with your integer state variable. For a value like step count, what we actually want to do is increment it. And if you just return a new value to it from a node, that value is not going to be, the existing value is not going to be incremented by the new value. It is just going to override it. So this will automatically become 5. That's how the default reducer works. That's how the default reducer works. So in cases where that's the behavior you want, you can just leave things as is. You can just leave it. You don't need to change anything. You don't need to write any custom reducer or use LangGraph's built-in reducers. Just leave it that way and it will just function fine. However, if you need data to be manipulated in your own way, you want to define how each state variable is to be changed, then you need to define something called a custom reducer. You need to define a custom reducer. Now, a custom reducer is basically a Python function. So whether you are using Python or JavaScript SDK, but it's a function. We're assuming Python SDK here. It's a function. Let's say change step count. So your default, your custom reducer rather, is a function. And that function will take 2 values. It will take in 2 values. Let me just put a center stage here. Let's bring this down. Let's bring the function here. Okay, good. So we have our function. Let me give you some color. So we have this function, and it's going to take in 2 values. The current value of that state variable and the new value being returned by a node. The current value of the state variable and the new value being returned by the node. That is what it's going to give you to work with. So you can then take this function, and inside this function, you can define how you want the update to be done. You can define how you want the update to be done. For our step count, we want to say return current plus new, because we just want to increment it by the new value that comes in. But you can define anything here. You can define anything, any strategy that you want your update to take, you can define it here. They're just normal functions. So anything you can do in a function, you can do it. So that's what you do here. That's what you do in your custom reducer. So this is how you define a custom reducer. It's basically a function. And once you have it defined, in your state definition, let's say this is a state definition, you need to annotate your state definition using the annotated class. You need to annotate it. So first you give it your data type. This is a list. Then you pass in your custom reducer. So you can just say custom reducer. Or I'm just going to say C reducer to manage space. So you pass in your custom reducer. That's how you set custom reducers. Once you have them defined, you set them using the annotated class. So that's how the reducers work. That's how reducers work. So you can either use the default reducer or use a custom reducer. Now, before we go into our demo, LangGraph also provides a reducer. There's a special reducer that LangGraph provides. And this is because a bunch of times you're going to be working with LLMs and you're going to be working with a list of conversational messages. So LangGraph provides a way for you to manage these messages, this list of messages, with a special reducer called add messages. Add messages. Special reducer called add messages. So LangGraph provides this reducer. If you know that one of your state variables is a list of LLM messages, just use add messages. Just use add messages. It's going to help you manage the entire chat history within your LLM interactions. So we're also going to be seeing how to use that in another video. Not in this video. We're going to be seeing how to use that in another video. But now that we understand how reducers work, let us go into VS Code and check it out. So now here in VS Code, let us have a simple demo of how we can use reducers with our agent state. Now the demo we're going to be using in this example starts with a function. We'll define a function that does something similar to what we did when we were working with agent schemas, which is a function that just builds a graph that we can work with so that we don't have to create a graph over and over again for the different examples that we're going to be working with. So let us quickly walk through this function. It's called run example, and it takes in a name. This is just a string name for the demo that we're doing. Then a state schema, which is a schema that we defined, and also a node func argument, which is basically the only node that we're going to be using in this example, which is a simple node that just updates the state. We're not going to be doing two nodes, or just one node is okay for this. And also we pass in an initial state for our example. So inside this function, we have a print statement here that just tells us the example that we're running. Then we create our graph with state graph by passing it our schema. Once we have that, we add our node, which is the only node that we're going to be using in this example. It's called update node. So we add it as node func, which is the argument that comes in from here. Then we start with an edge that goes from the standard start node to the update node. And then another edge which goes from the update node to the end node. So our graph is basically a straight line. It goes from start to update node and from update node to end. Then we compile our graph and generate a final state for our operation by calling invoke on our graph and passing it the initial state. Then finally, we just print out the initial state and the final state so that we can compare both. So that's basically our function, and we're going to be passing it our state, any state that we create, whether we're going to be creating state that doesn't have any reducer, and we're going to be creating state that has reducer. So we're just going to be passing that state definition inside. We're also going to pass the node that we use for the operation, and it's just going to help us run the graph. So to start our very first example, let us begin. The first example is going to be a state that has no reducer, a state definition with no reducer. Now our state will contain two state variables, two simple state variables, count and animals. Count and animals. Count is going to be an integer that we expect to increment, and animals is just going to be a list of strings. So we're going to be using both. We're going to be using these two state variables to define our state, and we're going to be looking at them with and without reducers. So first, let us start without reducers. So let's say without reducer. And to define the state, I'm going to be bringing some guys in from the typing library. That will be the annotated class, the list class, and the typed dict class. So bring those three in, and as you may have guessed, we want to use type dict to create our state. So I'm just going to create the state without reducers. I'm going to call it state without reducer. It's going to inherit from typed dict, and it's going to have two state variables: count, which, as I've mentioned, is just going to be an integer, and we're not going to add any reducer, so that'll be fine. We have an integer. Do we need? Oh yeah, we're not adding a reducer, so we don't need. Then we're going to have animals, and that will be a list of strings. So these are our states, and it doesn't have a reducer. There's no reducer added. That's why we didn't use the annotated class. There's no reducer added to this. Let us run this and see what we get. First, let us create the node that will help us update it. So I'm going to say node to update. It's taking our state, and this state will be of the instance state without reducer. So state without reducer, we're going to return a dictionary, because that is what we expect to return from our node to update the state. So return a dictionary, and inside here, we're simply just going to return updates. So for the count, I want it to now be 1. And for animals, I hope to add a cat. So count, update it to 1, animals, make a cat. So that's good. Finally, let us create the initial state that is going to be defining where our starting point, the starting point of our state. So we'll start with count. And let's say I want to start count from 5. And for animals, let's just have a lion and a buffalo there. So lion and buffalo. So I'm starting my count at 5. And for animals, I just have a lion and a buffalo. So with this, we can then run our example. We can run this example and see the type of update that we get. Let's scroll down. I'm going to collapse this. And just under here, I'm going to call run example. Not fun example, run example. I'm going to call run example. It expects a name. So a name, which is the name of our example. I'll set that to no reducer. Next is our state schema. And I'm just going to give it the state without reducer. That's the state schema we're going to be using. Next is our node function. And we're going to set that to the node function that we declared here, or we defined here. And finally, our initial state. We're just going to set that to the initial state variable that we created. So yeah, we have missing a comma here. Okay, good. So the name is no reducer. The state schema is the state schema that we created, which is state without reducer. The node function that we need is node to update. And our initial state, we've defined it to start count at 5. And the animals as the animal list as lion and buffalo. I want to update through our node to set the count, to increment the count by 1, and to add cats to the list of animals. So let's see what we get. So I'm going to pull up my command line, and then we can run our reducers file. So I'll say python reducers.py. Python reducers.py. Let's see what we get. Open no demo errors. And yeah, running example, no reducer. Now our initial state has count at 5, and it has animals as lion and buffalo. Those are the two animals in the list. But look at what happened with our final state. Count is set to 1 and animals is set to cat, which is the update that we sent in, which is the update that was sent in, showing that it just took the update that we sent and used it to override our existing state. It performed an update, but not the type of update that we want, and which is what the default reducer does. It just replaces what is existing with the new thing that is being returned. So you have to take note. If that's the behavior you want, that's totally fine. But if you don't want that, you need to define custom reducers for your state variable. Now, here definitely this is not what we want. We want count to be incremented, and we want our animals list to be to have the new input appended to the existing list. So for that, we need to write a custom reducer, and that's the example that we're going to be doing next. So let's close out of this. I run the second example. Let us write the second example. Let's write the second example. So with reducer. Now what we're going to be doing here is that we're going to be writing a custom reducer for our count state variable. Yeah, we'll do that first. There's another. We're also going to be using a reducer for our animals, but that's I'm going to be bringing a special function for that. But we're going to write a custom one for our count state variable. And like I said, to write a custom reducer is simple and straightforward. You basically use a Python function or a JavaScript function if you're using the JavaScript SDK. So what we're going to do is we're going to say define update count. We call that the name of our custom reducer for the count state variable, update count. And like I said, it takes the new, rather, it takes the current value of the state variable. That's the current value of count. You can type int based on the variable, based on the type of the particular state variable that you're trying to update. But for now, I'm not going to do that. I'm just going to say current. And it also takes the new value, which is the value that's coming from a node update. So it takes those two, and within your function, you can determine how they are updated. You can determine how the update takes place. So this can be as complex as you want. It can be as simple or as complex as you want based on your use case. For this example, we just wanted to add the 2. So increment the current value by the new value. Increment the current value by the new value. That's what we want. That is what we want to happen whenever we send in a new update for this value. So we send that, we do that. Then we come down here. I'm going to define another state schema. This time I will call it state with reducer. State with reducer. The first one was state without reducer. And by the way, let us comment out the example so that it doesn't run again. Let's comment that out. Okay. So state with reducer. We give it typed dict. And here we can say count for count. And this is where you use the annotated class, because that's how you add extra information to your variables. So you need to use the annotated class. Use the annotated class. And the first thing that goes in is the type. The first thing that goes in is the type. So it's type int. And the next thing that goes into this list is, or this definition, is your reducer. Anything you put here is going to be automatically recognized by LangGraph as the reducer for this state variable. Anything you put after the type int is going to be automatically recognized as the reducer for this state variable. So here we're going to add update count. And no, for animals, for now we're not going to add any reducer, but we're going to be adding one later. But for now, I'm just going to leave it as a list of strings. So now we have this state reducer, which is good. Now we can run our example. Once again. So I'm going to come down here and call run example. And for the name, we'll say with reducer. The next argument is our state schema, which now would be the new state we just defined, state with reducer. And after that, we are going to have our node function, which is the function that we also used there, node to update. And finally, we're going to have our initial state. Initial state. And we'll set that to the initial state that we defined here. So our count still starts at 5, and our animals list contains a lion and a buffalo. But now we are working with a reducer. Only for count for now. We're working with a reducer. So let's see how this would turn out. Let's pull up our command line. Let's clear this. And now let's run this example. So now we have our initial state, which has count at 5, and animals with a lion and a buffalo. But in our final state, we now have count at 6. And if you remember, our node updates our state by returning 1. Yeah, this is our node. It updates our state by returning 1 for count. And what our custom reducer did was that it took that new value, which is 1, and added it to the current value, which is 5. And now we have 6. So our custom reducer is in action. But we didn't specify any reducer for animals, so we still have it as cat. So with that, the default reducer is still in effect. But what if we want to also give that a custom reducer? For that, I'm not going to be defining the custom reducer. I'm just going to be bringing in a very wonderful library called operator. So we'll say from operator, import add. So I'm going to bring in the add function from operator. Then we'll come down here and say for this animals definition in our state with reducer, we want to annotate it. The type is still going to be a list of strings, but now we want to add a reducer by using operator's add function. So you can actually bring functions from other packages, whether custom packages or packages you pulled using pip. Yeah, as long as they are pure functions. And they follow the signature of state reducers. They have to follow the signature of state reducers. So animals, we have it as a list of strings, and now we have added the add function from operator. So let us save this, and now we can run the example once again. And pull up the command line. Let's clear it up. And now when we run our reducers file once again, initial state, count is 5, animals as lion and buffalo, and for the final state, count becomes 6 using the custom reducer that we wrote, which was already working fine. And now if you look at the animals list, you see that cat is now appended to the list. Yeah, cat is now appended to the list. It is no longer overriding the existing value. How amazing is that? So that's basically how reducers work in LangGraph. And like I said, LangGraph also provides this add messages reducer that you can use to manage messages from an LLM. So in this video, we're going to be discussing the special type of reducer that comes with LangGraph. Yeah, the special reducer that comes with LangGraph. In the previous video, we've looked at reducers. We looked at the default reducer, and we also looked at how we can create custom reducers. And reducers basically determine how our state variables are updated. Now, LangGraph provides the special add messages reducer, and we've seen it in some of the previous lessons. The main purpose of this reducer is to help you manage LLM conversations, LLM messages. Now, while you can build your graphs without any LLM, LangGraph is basically built for you to build LLM-powered applications. So definitely, you are going to be doing some stuff with LLMs. And your prompt response cycles with your LLM is most likely going to be kept in a conversation history, because your LLM needs to maintain context so that it can hold a conversation. It can hold a conversation, and it can also maintain the session of messages within the particular run of your graph. So you need to be able to structure these messages appropriately. You need to be able to put them in a list in the order that the messages are supposed to be, because when it comes to LLM conversations, there's a structure that the messages have to follow. You can't just bundle messages in a very random order into a list of messages. No, there's a conversational flow that the messages have to follow in the list of messages. And these and many other advantages is what you get when you use the add messages reducer. So, like I said, this reducer is meant to help you with LLM messages, and it basically handles three types of messages. So it helps you handle, I agree by default, a human message. A human message, you can also use it for, or rather, it also helps you handle base messages, which is the base class for any type of LangChain messages. You can also use it to handle AI messages and also tool messages. By the way, I don't think this thing have plural. So tool message, AI, let me correct that. AI message and base message. So basically the types of LangChain messages. So you can use it to handle these type of messages. And anytime you're having a conversation with your LLM, the add messages reducer is going to help you bundle your messages into a state variable in the right order they're supposed to go. And like I said, you can't just bundle messages into a list in a random order. It has to follow a particular conversational flow. So let's say, for example, you're talking with your chatbot, you're talking with your LLM. The first message you send as the user is a user message. So you send a user message. I think I did a box here. Let's do the box. Yeah, let's put a box here. So you have this. Let's make it transparent. So you as the user, you send in a prompt. You send in a prompt, and that prompt is a human message. I think I should duplicate this. Yeah, so that I can use them. So you have a human message. You send in your message. Then the LLM responds. The LLM responds to your query or to your prompt. So what happens is that the LLM will send an AI message. The response from the LLM is an AI message. Now, let's say you get that response and you want to respond back. You then send another human message. Send another human message. Then the LLM processes it, and let's say it realizes that, oh yeah, this particular prompt requires a tool, requires you to use a tool. So what happens? The LLM sends a tool message. It sends a tool message, and then you receive the tool call, you process the tool call, and you also need to bundle back the tool call to the model so that it can respond. So you probably would have two tool messages following each other. Then you send it back to the LLM, and the LLM then responds again with a final response, which is an AI message. So this conversation that you're having with the LLM has to be in a particular order, and that is part of what the add messages reducer helps you to maintain. You can also add something like, let's say at the beginning of your conversation, you add, okay, how do I pull this? Yeah. So let's say at the beginning of your conversation, you add a system message. You add a system message, which we know that for every conversation, you only have one of it. For every session with the LLM, you only have one of it. So yeah, you can also have a system message at the top here. And this is your conversation history. This is your conversation history. So the add messages reducer helps you to properly package this into a list of messages so that when you want to requery the LLM, you just bundle your conversation history back to the LLM and it can respond with context, because LLMs are stateless. So anytime you need to maintain a conversation, you have to always send back all the previous conversation to the LLM so that it can understand the context in which you are asking the question or you are sending the particular prompt. So what are some benefits of using the add messages reducer? Like I said, first, it is native to working with LLMs. So if you want to maintain your conversation history, just use the add messages reducer. Just use the add messages reducer. Don't try to work with strings. Use the add messages reducer so that your messages can be stored as LangChain messages. And when you construct other messages, probably messages that will involve other parts like media parts, you can always follow the standard structure, and your AI, your add messages reducer will help you manage the whole complexity behind every message that you're sending to the AI and what you're getting back. Now, what are some use cases of this? Definitely the one that jumps out is for conversational agents, because what the add messages reducer basically helps you to do well is that it helps you maintain your conversation history. Sometimes you can even merge two AI messages that kind of follow each other so that you don't have like two of them. It just recognizes that these two messages are from the model, so it just merges the two messages together and the history just flows. Also in agents, for sure, in AI agents, when it comes to tool calls, you are better off working with your add messages with user to help you package your tool responses in the standard tool message format. And also for human in the loop operations, whenever you had your own input as a human, it helps you package it as a human message into the conversation. So a whole bunch of benefits comes for the add messages with user. Whenever you're working with LLMs, just use the add messages with user. This is the LangGraph recommended way for managing your state of messages between you and the LLM. So now that we have an understanding of what it does, let us jump into VS Code and see it in action. So in this video, we're going to be running a simple demo to show how the add messages with user works. And we're actually going to be using an LLM. We're going to be using an LLM. In previous examples that we've done, we didn't actually use an LLM. We just kind of showed add messages using simple messages that we had coded. But here we're going to be using an actual LLM. So first, I'm going to pull up my command line. Let us make sure that we are inside our virtual environment. So I'm just going to activate that. The source VMV bin activate. Okay, so now we're in our virtual environment. And the next thing we're going to do is to install the LLM SDK that we're going to be using for LangChain. And I'm going to be using OpenAI. Feel free to use any LLM provider of your choice and use the LangChain wrapper, but I'm going to be using that of OpenAI. So I'm going to say pip install LangChain OpenAI. Pip install LangChain OpenAI. That should install very, very fast. And also know that for you to use any LLM of your choice, you will need the API key. So for me, using OpenAI, I'm going to be adding the OpenAI API key to my environment, which is the next thing that I'm going to do. If you're using Gemini, make sure that you had that. And if you're using Anthropic or Grok, also make sure that you had the necessary credentials. So I'm just going to add the OpenAI API key. Say OpenAI API key and set it to my API key. Now your API key is a very sensitive object, so it is not something that you should expose. So I'm just going to go and come back and I will have added it to my environment. But just know that this is how you add it. If you want to add it to your terminal, export OpenAI API key, that's the name of the environment variable, and you set that equal to your OpenAI API key. So now I've added my OpenAI API key, so I can authenticate with the API successfully. So we have those in place. The next thing we're going to do now is to create our file. So let me just close out of this for now. We'll create our file. And I'm going to call that add messages demo.py. Add messages demo.py. And here we're just going to be creating a simple graph. A simple graph that just has a node. The node uses an LLM. We send a message to the LLM. It sends a response. We get the final state. And we can keep sending messages to the LLM. And it will kind of function like the back end of an AI bot. Yeah, that's how it's basically going to function. So we have the graph in session. Once the graph is in session, we can send messages to it. The node is going to have an LLM that is going to take in our messages, process it, return a response, which will be our final state, and we can continue to tack onto that conversation history and get new responses. So first, let's begin by importing some necessary libraries. So first, we want to get from annotated. From typing rather. You want to get annotated. Yeah, I knew something was off. Yeah. From typing, import annotated. Then import typed dict. And list. Type dict, annotated, and list. So those are the classes we're going to be needing from that model. Next, we're going to bring in our graph classes. So say LangGraph.graph. The first thing we're going to bring in is state graph. Then we also need our, I keep missing import. Why? What's going on today? Import state graph start and end. Yeah. Now once we have this in place, the next set of items we need to bring in are the messages tools, the message tools. I'm going to say from, oh, I have caps lock still on. From LangGraph .graph .message. I'm not going to miss import this time, and this is where we bring the add messages with user from. So you can find the add messages with user inside LangGraph graph message. Now, just to keep things standard, I'm also going to be bringing the LangChain messages that we're going to be using to define our state. So LangChain core, from LangChain core.messages, we're going to import base message, and human message. We're going to be using base message to define our state messages variable. That's where we're going to be storing our list of messages. And we're also going to be using human message to send in our messages. Now, the next thing we're going to do is to define our LLM. Let's set up our LLM. For that, we need to import a class. So I will say from LangChain OpenAI, import chat OpenAI. Yeah, that's our wrapper class for working with OpenAI in LangChain. So we're going to get this, and we give it our model, the model we want to use. I'm going to go with GPT 4o. So LLM equals chat OpenAI, and we're going to be using the GPT 4o model. So that's good. The next thing we're going to do is define our agent state. Let us define our agent state. So I'm going to say class agent state. Going to take in typed dict, and we're going to have a messages key, because that is the key that add messages works with, messages. So we're going to take a messages state variable or state key. It is going to be a list of base message. List of base message. I forgot to put annotated. Yeah, annotated list base message. And the reducer is going to be add messages. Add messages. I think I'm missing some. Okay, yeah, I have extra brackets. Okay, let's get rid of those. Okay, yeah, now everything looks clean. So we create our agent state, which is using a type dictionary so that we can use type ints, and a messages state variable that is going to hold our messages. It's going to be a list of base messages, which are the standard LangChain messages for LLM messages, and our add messages with user. So this is all set. We've now set up this state variable to use the add messages with user. The next thing we're going to do is to create that node, that LLM node that is going to be taking our input and going to be calling an LLM, and the LLM is going to return an AI response. So let's do that. Nodes are functions, as we've learned in previous lessons, though we still have a video coming up on nodes. So yeah, that is going to give us more examples of nodes and how to construct them. We're just going to call this chat node, the chat node, and chat node is going to take in the states, and that state is going to be agent state. So chat node takes in agent state, and our chat node is going to return a dictionary. So that's good. What do we want to do in this node? What do we want to do? Definitely want to take the input, and we want to call the LLM to process the input and return the output into the state, into the messages variable in state, so that the conversational history can be maintained. So let's do that. The first thing I'm going to do is get the conversation history. Get the conversation history, and that's going to be state messages. So that's our conversation history, and we're just going to say response equals LLM, which is a runnable, so we'll call .invoke on it, and just pass it the conversation history. Just what is the conversation history. So like I said, LLMs are stateless, so you always need to pass in the entire conversation history for it to give you a reasonable answer. And since we are creating something like a chatbot, we need to always send the entire conversation history in. So whenever you add a new message and you run this graph, the new message is going to be inside the messages list, and then we can then push that entire conversation history into the LLM and get a response. So once we have that, we can then return our state. I'll just say messages and give it the entire response. Oh, sorry, messages in quotes. So say messages and give it the entire response. And that way, response. So that way, add messages is going to take care of the entire thing. Because you might be wondering, isn't there duplication? Don't worry. That is one of the advantages of using add messages. There are duplications, it's just going to take care of the entire thing. It knows the order of the messages and is going to arrange it the way it's supposed to be. In an idempotent, in an idempotent manner. So nothing is going to be repeated. Nothing is going to be duplicated. So yeah, we'll just give you the entire response, and add messages is going to take care of it. So this is our chat node. Now we can build our graph. Now we can write our graph and use this chat node to process our input messages. To build the graph, let's come down, and we're just going to say graph equals state graph. Then we pass in our agent state. Which is good. And we add our node. So I'm going to say graph.add node. We add our single node, which is the chat node. So we add chat node, which is good. Now let us construct our graph by connecting all the edges. So the first thing we do, we first say graph.addEdge. There's also a whole video coming out on edges where we get to see more edge examples and how to construct them. So that'll be fun. So we say add edge, and we start from the beginning and find our way to chat node. And from the chat node, we simply terminate the graph. Yeah, simple and straightforward. Our graph is basically a straight line. So it goes from start to chat node, from chat node to end. That's all. We just want to send a message, have the LLM respond, and want to get a response. And you can, like I said, that can be a backend for a chatbot. So you just keep sending in messages and it will respond, and you are sure that the conversation history is maintained. So every response you get is actually aware of the conversation history and produces relevant responses. So that's good. We have it ending, and the next thing we're going to do is to compile our graph. So I'm just going to call that agent. So we're building an agent. Compile the graph. Graph.compile, and we're good. We're good. We have our chatbot agent. How awesome is that? Just 31 lines of code with spaces, and we have a whole conversational bot. So yeah, we have the agent here, and we can send messages to it. So let us do that. Let us send a couple of messages into it and see what we get. Our first message, let's call it message 1. Message 1 is going to be a human message. I'm going to say, hello, my name is FK. Hello, my name is FK. So what I will then do is say the first turn of this conversation, I'll call it turn state 1. So the first conversational turn 1 state. The first turn of this conversation will be me invoking my agent, which is also a runnable. So I'm going to invoke the agent by passing in keep forgetting the quotes. So messages, and I'll set that to my message. Set that to my message. So that is the first message I want to send to the agent, and I just simply send it to the messages list. Now I didn't even have to put this as a list or and all. Add messages is going to take care of that. So we get this, and now we can print out. Print this out. I'm going to say graph after first run. Let's put some dub around there. Graph after first run. And here we just simply print out turn one state. And just to put a delimiter, because we're still going to be running another example, just going to put that 30 dashes under here. 30 dashes under here. So yeah, that's good. We have built a graph, a simple chatbot, and we are passing it our first message. Remember, we're using an LLM powered by OpenAI, and if you're going to do that, you have to make sure that your API key is in place. So we built this simple graph. We sent an email message to it and want to see how the state looks after the first turn. So let us run this example and see what we get. So command line, something. Okay, I think I pulled this up mistakenly at some point. Okay, now let us run this example. Put it up a little bit. Let's say Python add messages demo. Let's hope everything works fine. It's calling the OpenAI API, so that will take some time. And yeah, latency over. We now have our response. Awesome. So we have graph after first run. And as you can see, we get our state back, which only has one variable, which is the messages list. This is the list. Is a list of messages that can be a human message, AI message, tool message, and the likes. Now, what we get inside this list, first we have our human message, which is what we sent. It says, hello, my name is FK. Then we have the other additional configuration stuff. That ends here. We have the ID of the message, no keyword arguments, and yeah. We have our human message that was sent first. Then we have the response from the AI, which is the AI message. We have an AI message here. And it also has a content property. And the content says, hello FK, how can I assist you today? Hello FK, how can I assist you today? And unlike our human message, it comes with a lot of baggage. So it has additional keyword arguments. For example, we can see the details for the token usage. Completion tokens are 11, prompt tokens were 14. So I actually spent more tokens prompting it than the response. Interesting. Then we don't have any reasoning tokens because we didn't use the reasoning capabilities. 4 is a reasoning model, yeah, but we didn't use the reasoning capabilities, so we didn't get any tokens in that aspect. We didn't use any audio tokens because we didn't do anything like that. And yeah, so you see how getting our response back, and it's coming in the proper structure that is required. So this is our first turn. Let us run another message through this chatbot and see if it can recognize the context, respond appropriately, and also make sure that our conversation history is properly maintained. So first I'm going to just clear out of this and just close this. So for our second example, let's come down here. Just going to say turn 2. And for that, we're going to create message 2, which will also be a human message. Passing content. By the way, you can actually send these messages as strings. Add messages is going to take care of bundling them as human messages. But, you know, sometimes you just want to code in a very standard way. So we're using the standard human message constructors. And sometimes also, for example, for a human message, you probably want to add different parts. So you want to add something like maybe you want to add an image. So this helps you to have different parts of the message. Then we will not have content as a string. Content will be a list of different parts, and those parts will represent text part, which is the normal text message you send. And you can also add audio, you can add images. But for now, we're keeping it simple. So we'll just say content, and we'll say, what is your favorite color? Yeah, we're asking the model what is its favorite color. What is your favorite color? Let's see if the model will answer us, or it will tell us that it doesn't have emotions and all that, yada, yada, yada. So yeah, we have a message 2. Then let us get our state for the second turn by running this message through our chatbot. So I'll say turn 2 state equals our chat agent invoke. Then we pass in our input messages. Now, for you to keep the conversation going, you have to make sure that you get the previous state and add it to the new incoming message. So I will need to say turn one state messages and add it to message 2. Add it to message 2. Now, so we get this state. We take messages because now we're creating a new input. We're creating a new input into this invocation. Assuming we add multiple nodes, we'll just use the add reducer function is just going to take care of all that binding of the previous state to the current state. But this one we're running it as if we're running a new request to the model. So get turn state 1, we add message 2, and now we can come down here. I think I'm just going to copy all these guys. Copy these guys and copy here. But this will be turn 2 state. Yeah, no, not that. This is going to be turn 2 state. Yeah, and this will be second run. So graph state after second run. Put state. Graph state after. Okay, so that's good. Now let us see what we get from this. So I'm going to pull up the command line once again, and we run our file. So run our file. Boom, boom, boom. Yeah, this is the first one, the first run and the second run. 2 runs complete. Perfect. But we are interested in this second one. So graph state after second run. So we have our conversation history. We still have our human message here. We have that AI message that we sent in, that we got back previously when it tells us, how can I assist you today? And after that, if we go down, the first AI message is done here. No, I think, yeah. So the first AI message is done around, I think somewhere here. Yeah, good. Somewhere here. Then we sent our second human message, which is, what is your favorite color? Yeah, what is your favorite color? Then, what do we get? Our AI message, once again, and a new AI message that tells us, I don't have personal preferences, but I'm here to appreciate and discuss any color you like. Do you have a favorite color? So yeah, the soulless chatbot responds. But yeah, as you can see, we are maintaining our conversation history. And for a chatbot, you can just wait for messages. You can use something like a while loop to wait for messages. And every time you get messages, you just send them back, send them into the into this graph state, and it's going to update the conversation history. It's going to send back the new conversation history, and the chat is going to provide a relevant response. And if you type another message to run again, and it just keeps running and keeps running and keeps running and keeps waiting for new messages and keeps responding to new messages that you type in. So yeah, that is the add messages reducer in LangGraph. Now in this video, we're going to be discussing how to manage messages in graph state. We're going to be walking things from simple to standard. Yeah. And definitely, as usual, we're going to be wrapping things up with a demo where we can see the tools that LangGraph rather provides for us to work with messages. Now, as we all know, there are 3 common messages. We have the AI message. Or rather, let's start from the human message. We have the human message. Now, the human message is the message you send. Any message that comes from you, or probably you type into the system to be sent to the LLM, that is a human message. That is a human message. So either it is coming from a real human input, or your application is actually sending the prompt directly to the LLM. That is considered a human message. Then we have an AI message. We have an AI message. And an AI message, also called an assistant message, is basically your response from the LLM. That is your response from the LLM. So the response you get back from the LLM, whichever mode it is, text, image, whatever, that is the AI message. That is an AI message. Now, we also have a tool message. We have a tool message, which you can argue is a subset of an AI message because it is also a response by the LLM. But this is the tool suggestion or the tool call object that the LLM sends. So if you provide tools in your LLM call, and the LLM analyzes the prompt and says that a tool is necessary, it's actually going to return a tool message. It's going to return the suggestion for the tool to call and also the arguments that you have to call the tool function with. So we have the tool message. There are also other messages like system message. Let's put system message there because it's also very useful and powerful. So system message, this for you to kind of like give instructions to the model at the very beginning of your conversation, so that instruction kind of carries through the particular request or even the entire conversation that you have. So for example, let's say you want the LLM to, for some reason, always answer you in French. So at the beginning, you can set a system message and tell it that give me all responses in French. So yeah, those are messages. And there are different ways you can manage them within your graphs. Now, to manage a set of messages, you need a state variable to hold the messages. And the state variable is definitely going to come as a list, because you are going to be holding, or most likely going to be holding, more than one message. So you are going to have a list to hold your message. So let's say you have your agent state, and within your agent state, you define a state variable called messages. So you can set that to list. You can say a list of strings. So this is one way you can define the variable that is going to hold your LLM messages. This is just a simple way. You want to hold them as strings and nothing more. Fine. Now, if it remains this way, you are using the default reducer. So you won't be able to actually have a conversational history. Every new message is going to replace the previous one. The previous one. Or any new list is going to replace the previous list. So if you want to be managing it that way, where you just swap in the entire new list with the old list, if that is what your use case requires, then fine. But most likely not. You would often need to provide a reducer. You need to provide a custom reducer. Specifically, because this uses the default reducer. So you need to provide a custom reducer. And one example is something like the add operator, the add function rather, from the operator library. So to do that, first you have to annotate this definition, and then you come here and add the add function as your reducer. Well, let's just say operator.add. So operator.add. Yeah. So you say operator.add, and that way, anytime you add a new item to this list, it will be appended to the list. It's not going to override the entire list. It's going to be appended to the list. So that's all fine and good. This way, you don't get your whole conversational history just wiped off. However, with something like this, you won't be able to for you to work with two messages is going to be a bit difficult, because two messages are not plain strings. They are structured as a part, a prompt part or a message part that has a particular structure that it has to follow for the LLM to be able to read it. So if you're going to be using two messages, this probably won't work. So you want to go with something like the LangGraph add messages reducer. Because it helps you to work with things like two messages. It also helps you to properly handle human in the loop. So anytime you have that interruption whereby you can intervene in the model's operation, add messages will help you to convert whatever you put in, whatever your input is as the human. It will help you to add it to the conversation history as a human message. So yeah, now this is our structure. This is what we're working with. We have add messages, and this is definitely okay. This is perfect. This is wonderful for you to use as the state variable definition in your graph. Now, because this setup is very common, LangGraph actually provides a class called messages state. Yeah, messages state. So we have its messages state. And yeah, now before we talk about messages state, one more thing here. So by the time you start using add messages, it's better you define this as a base message. So once you start using add messages, this becomes base message, because you now don't have a list of strings. You actually have a list of message type. You have a list of standard LangChain message types, so that when add messages is adding to this list, there won't be any errors. It won't throw an error. So have base message, and we're using base message because it is the base class for every type of message in LangChain. Yeah. Now, when I see me saying LangChain, I was like, are we not talking about LangGraph? Yeah, messages come from LangChain. Message definitions come from LangChain. And even when you are bringing in their classes, they're going to be from the LangChain package. But once you install LangGraph, it already comes bundled with LangChain, so you can actually just pull any of the LangChain classes that are in the core package, not the ones in the community or the ones that are from other specific vendor packages like LangChain OpenAI or LangChain for Google Generative AI. So base message is going to apply to any type of message, so that when add messages is adding any type of message, be it tool message, human message, or any type of message, this applies. So then this whole setup, LangGraph provides a messages state class. A messages state class. You can just use this class as your state. If you would only have messages, if you only be working with LLM messages, you can simply just use this class as your state. So you can do something like this. You can just say your graph should be equal to state graph, and you pass in messages state. Passing messages state. Yeah. And all this is available to you. You have all these already. You don't have to write every single thing here. You have a messages key in your state. It will be annotated. It will be a list of base message, and it will be using the add messages with user. So yeah, that's just a lovely helper for you to do that. But sometimes, in a lot of times, actually, you don't just want to keep messages in your state. You want to keep other things. Yeah, you want to keep other things. You want to keep other state variables in your state. And you want to, let's say you still want to take advantage of this messages state class. So what you can do is that you can define a new agent state. You can simply just define a new agent state. And that agent state is going to inherit from messages state. To inherit from messages state. And that way you already have all this entire setup. So you don't have to write all this. You have this entire setup. You already have a state variable that's going to manage your messages, and it uses the add messages with user. And you can go into your class and still go ahead and add other variables, like say step count. Can add other variables like step count, and just keep adding all the variables you need in your state. So yeah, this is how you can actually take advantage of messages state and also still use your agent state class in the usual way, adding other variables that you might need. Now, this is all about setting up messages, setting up a state variable for you to handle your messages, and making sure that your messages are properly handled. But what about accessing messages? How do you access messages in your state? So for accessing messages, let me just use this area. So let me bring this guy here. Let me use this area. Now, messages appear in state in two ways. They appear in state in two ways. So in your list of messages, so you have your state, you have the messages key. So in your list of messages, you have the list, and they can either appear in the class form. Let's say human message content. My message content equals blah blah blah. So human message content, so they can appear this way. That's one way they can appear. And let me just copy this and duplicate it. Another way it can appear is not using the class syntax, but using the dictionary syntax. So you have another dictionary in here. And let's say for your first message, which is a human message, it will have a row key, and the row will be set to human. Then it will have a content key, and that will be set to what your message is. Yeah. So your messages can either be stored in your messages state variable this way using the class syntax, or this way using the dictionary syntax. So either way, you can actually access them the same way. So if I'm going to access this, I'm simply going to say state messages. So I get my messages key from state. And let's say I want to get, let's say, the last message, the very last message, say -1, and say .content. Because content is actually what gives you the textual representation of your message. So if you want to access your state message, you just say state, get the messages key. I want to access the last message, so I'll say -1 and .content, and to give you the string representation of your message, of your actual message. It can be, and that can be a human message, a system message. I don't know how a tool message is going to come out, but I believe it will still be in the content key. So probably that will return a dictionary of the content of the function call definition. So yeah, but everything is going to be stored in content. So yeah, that's your beginner crash course in messages in graph state. Now let's go into VS Code and write some code. So in this demo, we're going to be taking advantage of that messages state class. Yeah, we're going to be taking advantage of that because in previous examples, we've actually been writing the whole thing, the whole messages definition with a list of base messages and also using the add messages with user. But now we're going to be taking advantage of the messages state class and also adding like one extra state variable to the mix. We're going to be doing that, and we're basically going to be showing how to access the state, how to add messages, and also how to update another state variable that is not part of the messages state. So we're actually going to create one node for each of that. So our graph is just going to run through all the nodes. One is going to access state, one is going to add to state, that's the messages state itself, and the third one is going to update the other custom states that we are using in our messages state. So let me stop saying state all the time and just get to work. So let's say messages state demo.py. Let's start that way. The first thing we're going to do is to bring in our classes. So first with the classes that will help us in defining our state. Say from typing, import, annotated, typed dict, and lists. So to begin, first let us bring in our graph classes. So I'm going to say LangGraph.graph, import, we need state graph, we need start, we also need end, and our magical messages state class also comes from this package. So let's say messages state. So that's good. I spelled state graph wrong. Yeah. So state graph, start and end. Those are the things we need to create our graph. So next we're going to bring in some message classes from LangChain core. So it's LangChain core.messages. Like I said, messages belong in the LangChain package, but installing LangGraph gives you access to it, so you can always pull in the classes. So say from here you should import. And for adding messages, we'll need a human message. And for adding an AI message, for working with an AI message, let me just use an AI message. Because in this demo, we're not going to be using an LLM, we're going to be adding a fabricated AI message. Yeah. So we get these two in. Now let us continue. So the first thing we're going to do is create our state class. And I'm going to call that my graph state. And like I said, we're going to be making use of the wonderful messages state class, which gives us access to a messages key and add messages automatically. So we'll say messages state. We're inheriting from it because we want to add another variable into the mix. So for here, I'm just going to say turn count int. Yeah, let's just yeah, we'll know what that does later. So yeah, turn count an integer. Just put that in. Now let us add our nodes. Let's add our nodes. And like I said, we're going to add a node to demonstrate how we can retrieve states. We're going to add another node where we're going to show how we can append to our message list. And I'm also going to write another node where we just simply update turn count, just to show that, yeah, you can also update other variables aside the messages variable that comes with messages state. Start with the node that adds a message. I'm going to say define user node. Define user node. It will take in states, which will definitely be an instance of our graph state. This node is going to return a dictionary, which is kind of implied at this point. Well, let me do that correctly. So here we can then, I'll just put a message here first so that it can appear. We can see the process in our command line. We can see which node is running. So executing user node. Let me put it in quotes. Executing user node. So executing user node, and what we'll simply do here is to add a user message to our state. So I'm just going to return messages, and I'm just going to set this equal to a human message. Content equals. For this, I'll just say, what is the weather like today? What is the weather like today? So that's good. No, come on. So that's good. That is a node that adds a message. Now let's create another node. I'm going to call it AI node. And this node is going to do two things. It is going to access the previous state. It's going to access our messages key in the state, and to also add our fabricated AI message. So it kind of be like the response to this question. So let's put graph state again. My graph state. Just going to assume the dictionary part of this function because we already know it returns a dictionary. Now inside here, first I'm going to say print executing AI node. AI node, so now we know that this is what we're currently doing, and we're going to access. Let us access our state. Let us access the last message in our state. So I'm going to say last message, and I'm going to set that to state messages. I'm just going to say -1 dot content, and we're just going to print this out. I'm going to say human prompt. Let us use f-string so that we can have that variable in here. So last message. So yeah, human prompt last message. And now let us fabricate our AI response to this message. First, I'm going to say response content equals, and then I'm just going to write a goofy message where I will say, I have received your message, which is last message. I've received your message. Let's close this. I've received your message. However, I am a fake response and can't respond. Then I'll put a new line here and say, but at least my code is working. But at least my code is working. Oh, we have, okay. So yeah, that's the response we're going to give. Yeah, we will receive the human message, but we can't respond. It's a fake AI. So, but the code is working. Things are working. So we can return this and tack it on to messages. And we just set this to an AI message. An AI message where we can set the content to be equal to this. Yeah. So that's our AI node. It just creates a fake response and we tack it onto our messages array, or our messages list rather, as an AI message. So that's good. Now, the last node we're going to create is the one that just simply updates the turn count. Yeah, turn count variable. So it's for every turn, not for every node hop. It's for every turn. So it's going to be the last node, and it's going to register that. Oh yeah, this turn is done, so I can register 1. Then if you run it again, 2. Run it again, 3. So it's basically be incrementing. So let's define that. Go and call it counter node, which will also take in state. State being an instance of my graph state. I'm also just going to assume the dictionary that will be returned. And inside here, I'm going to print and say executing counter node. And we can simply return an update to turn count. So turn count. We'll also access our states. Say turn count. This is something that could have used a custom reducer from operator, but I'm just going to do it manually. So say +1. Yeah, turn count +1. Turn count starts at 0, right? Yeah, we'll define that when we initialize the graph. So yeah, we have this and everything looks fine. We have our 3 nodes. Now let us build our graph. So we come down here. So say graph equals state graph. And let us pass in our agent state, which is my graph state. Let's pass this in. And next thing we're going to do is add our nodes. So let us quickly do that. Graph.add node. Now you can just add your nodes with functions. With the functions, it will assume the name. So I'm just going to add them that way so we can run through this quickly. So we had add node, or rather user node, graph.add node again. And the next is going to be our AI node. And we can also say graph.add node. Give this our counter node. This is good. That is good. Now let us connect everything with edges. Let's connect everything with edges. We're going to start, go to the user node, go to the AI node, then go to the counter node and terminate. So let us run through that. So graph.add edge. Say start. From start, go to user node. Then let me just copy this and let's edit. So then we go from user node to AI node. After that, we'll then go from AI node to counter node. Counter node. And finally, we can go from counter node and terminate our graph. So from start to user, user to AI, AI to counter, counter to the end. So yeah, we have our graph, and now we can compile it. So let's call it agent, and let us take the graph and call the compile function. So we now have our graph returned as a runnable, which we have called agent. And now we can pass inputs into it. We can pass input into it and run different turns. So for this example, I'm just going to be running 1 turn. So I'll create an initial state. We don't need to do anything for the messages variable. The whole messages state setup is going to handle that. So we only need to have turn count with its initial value, which I'll set to 0. We can then say final state. Now final state will be us invoking this agent with our initial state. We can then print the final state of this operation. Let's have final state and simply print that. Final state. Print final state. Perfect. So let us run this example. Yeah, we've been building for quite a while, Now let us run this example. Let us pull up the command line, and now say Python messages state demo.py. Hoping the demo gods are behind us so that we don't run into any errors. Yeah, boom, everything runs quickly. We use a fake AI message, so as we were calling an LLM, definitely there will be some latency in between that. But yeah, let's see what we have. Executing user node, executing AI node. When it got into the AI node, it accessed the human prompt, which says, what is the weather like today? And then it executed the counter node. At the end of the day, the final state that we have is, we have our messages. You see, that messages array is already there. You don't need to put it there. So inside our messages, we have the first human message that we sent, which is, what is the weather like today? And then we have the AI message that we sent in. And if we look at that AI message, if we look at the contents property, it says, I have received your message. What is the weather like today? Which is what came from here. And it says, however, I am a fake response and can't respond, but at least my code is working. Awesome, awesome, awesome. And as we can see, turn count incremented to 1 because we went 1 turn. Turn count incremented to 1. So in this demo, we've seen how to take advantage of messages state. We've been able to use it to manage our message sequence. If we're using an LLM, we'll seamlessly manage our conversation history. And we also saw that we can actually use it within inherit it so that we can have other variables in our state class. And we've been able to see that with turn count, and we can also update that state variable alongside our messages state variable. Now in this video, we're going to be looking at LangGraph nodes. LangGraph nodes. Now, if you've been watching other videos in this LangGraph fundamental series, we've been using nodes a lot. There's no how you can build a graph without nodes. Nodes are basically the core of graphs. So you're definitely already familiar with nodes, but in this video, we're going to be taking a deep dive or a deeper dive into nodes. Now, nodes are primarily the action takers in a LangGraph graph. So let's just say we have a graph like this. So let's say this is our graph. And our graph is going to consist of one or more nodes. And these are basically the processing units within our graph. This is where actions take place. If you need to call a file, or if you need to read a file, this is where you do it. If you need to call an API, this is where you do it. If you need to call an LLM, this is where you do it. Every single processing you need to do, this is where you do it. So just think of nodes as basically functions. They are functions, and what you basically do is that you call them in sequence or in parallel based on the kind of workflow that you want to perform. But every single processing in a LangGraph graph is done in nodes. And as we've seen in other videos, nodes are connected with edges. You will see later that we can even have some nodes that are not connected with any edge, but you can just navigate them dynamically. But that's for another video. But nodes are basically the action takers in LangGraph. That's where you do all your processing. Every single action you want to take, every single tool you want to use, you do it in a node. And node represents, they also represent steps in a particular workflow. They represent steps in a particular workflow. So let's say you want to draft an email, or rather you want to send an email. So first, you probably have a node that takes input and processes it. So once that node is done, it then routes to another node, and the node composes the email. That other node composes the email. Then the next node sends the email. So that's how you compose nodes. So you put your unit actions, the unit actions of your workflow in nodes, and you connect them with edges in the sequence they are to follow. Or if they are to operate in parallel, you also make them run in parallel. So that's basically what nodes are. And in the background, LangGraph converts nodes to runnable lambdas. So if you have gone through the LangChain series, our LangChain series, you will definitely know what runnable lambdas are. And runnables being the core data type, so to speak, in LangChain. And also, if you think of nodes in terms of runnables are a unit of work. Yeah, a unit of work. And they take an input, they return an output. They take an input and return an output. Now, typically for nodes, they take in state and they return an update to state. We've already looked at state in LangGraph. So nodes basically take state, they read it to do their processing, and they also return an update to state. And if they have no update, they can simply just return the entire state and everything just remains as it is. But in this video, we're going to also be seeing some other things that nodes can take in. But basically, nodes behind the scenes are converted to runnable lambdas, so it makes them possess all the features of runnable lambdas, the async features, the functions you called, invoke, batch, stream. So all those properties, nodes inherit them naturally. So that's nodes in LangGraph. And because they're runnable lambdas, they also take advantage of all the tracing capabilities that come with the runnable architecture. So you can use, if you plug in something like Langsmith, it's just native to LangGraph to get you your tracing data and to also perform other observability functions for your LangGraph agents. So, like I said, nodes take more than state, but let's just look at the three things that nodes take. So, first, they take state. They take your graph state. So when you define a node, and to reiterate, nodes are basically functions. Nodes are functions. So if you're using the Python SDK, nodes are Python functions. If you're using the JavaScript SDK, nodes are JavaScript functions. So nodes are basically functions. And they take in state. They take in state. That is the default argument that you find in every node. So if we say if we define a node, let's call it node A. We say we define a node A. That node A can take in state. Let me move this down. I move this down, yeah, so that we can have this here. So we don't have to squeeze it to the side. So let's say we define a node A. Our node can take a state argument, which is of the type of our state schema. That's the state schema that we defined. So let's say we called it state schema. So it will take in state and it will be of the type of the state schema that we defined. Now that's the default thing that every single node takes, and is always the first argument. It's always the first argument to your node. And when you inside your node, you can do any type of processing you want. You can do any type of processing you want. You can access state variables by, let me get out of here. You can access state variables by saying state and key. So whatever key your state variable is, you can use it to access the state value in inside your node. And you can use that for any of the processing, any sort of processing that you want to do inside the node. So this is basically how you read state. And if you want to return, if you want to update state, you simply return your update, use the key of the state that you want to update, and a new value that you want to update the key in state with. So these are your update state, and you don't need to return the entire state. You just need to return a dictionary of all the properties that you want to update. So key, let's say I want to update key, and I want to also update key 2. So I'll say key 2, and that will be, let's say, new value 2. So you simply just return only the properties that you want to update. That's how you work with state in your nodes. And everything within your node is the same way you work with any Python function. Just do your processing the same way you're going to work in any Python function. But you know that whenever you want to write your return statement in the Python function, you are returning an update to the state, and it would be a dictionary of the properties and states that you want to update. Another argument you can have in your LangGraph node is config. Yeah, you can have a configuration. You can send in a configuration into your LangGraph node, and that will be of the type runnable config. Runnable config. So you can send in a runnable config into your LangGraph node, and you can use it to store configuration parameters. Even though I checked the new documentation that is coming out for LangGraph, that's the 1.0 for the version 1.0, and they are beginning to favor the next thing we're going to look at that you can have in your in your nodes. That's the context schema, which we're going to be looking at next. They're beginning to favor it for configuration over config, at least for runtime configuration. But you can also use runnable config to pass in configuration values that you can use for each run of your LangGraph graphs. So you can take in config. Another thing you can take in is context schema. Or let's just say context. It's context. Let's It's time to get this guy and move it in here. So I'm going to replace runnable config with runtime schema. So you can also pass in your runtime schema, which I said it's the preferred way now to pass configuration to your LangGraph nodes. And basically, what are these configurations? It's just values that you want to remain static within each run of your node. They are not state variables that change. They are not going to change. They're going to remain persistent through each run. So you can set defaults for them, and you can also override them when you want to invoke your graph. You can override some of them when you want to invoke your graph. So the context schema is, to me, kind of cleaner than runnable config, even though runnable config is still more elaborate, coming from the whole LangChain framework structure. But runtime context is much cleaner to work with. So for runtime, you basically pass in an annotated runtime. You annotate it with the context of your runtime. Let's say runtime context. So we're going to be looking at this much later. It has its own video, so we're going to be looking at it much better later. But basically what you do is you use the runtime class and you annotate it with the runtime context schema. So just like you define your state schema, you also define a runtime context schema and use it to annotate the runtime class. And once you have it in, sorry, this is runtime. It's a runtime, not this runtime, not context schema. Context schema is for when you want to invoke it. So this is runtime, not context schema. This is runtime, not context schema. And whenever you want to access your runtime, let's say you store, let's say database URL there, you say DB URL, you simply access it as runtime.context.db URL. So if you have defined a DB URL in your context schema, this is how you access it. So I can say URL, let's say MySQL URL. MySQL URL equals runtime context DB URL. So that's how you access. Let me lift this up. That's how you access your context schema. So that's how you access your context properties. So those are the three arguments that your nodes can take. State, which is the de facto argument for your nodes. Then we have config, which you can use to pass in a runnable config object, and also runtime context, which we're going to be looking at. We're going to be looking at the three of them basically. So now let us, before we go into Visual Studio Code, let us look at some default nodes that come with LangGraph. Now, the first default node is the start node. There's a default start node that comes with LangGraph, and the main purpose of the start node is for you to define the starting point for your graph. Yeah, it defines the starting point for your graph. So you want to say, this is the first node to call. So let's say you have a node A. You say from start to node A. So it marks node A as the entry point for your application. That's why most of the initial nodes are for collecting input from the user. But yeah, this is how you point to the node that you want to start with. And you can also point to a bunch of nodes in parallel. But the start node is for you to define the node that is going to be the entry point, the node or nodes that are going to be the entry point for your application. Then we also have the end node. And this is your termination node. This is where you say graph run complete. So as you build your graph, let's say you go from this node, then you go to that node, go to this node. Then when you get to this node, you want to terminate your operations. So what you basically do is go from this node to end. So let's put start here. Let's say start. So for start, you go from start to this node. So you say start at this node. Then this node does its processing. It updates the state. Then the LangGraph moves to the next node, which is connected to this first node with an edge. It moves to this node. This node does its processing. Then it returns some updates to state, or just returns the state. Then it comes to this node. It is done. The email is sent. We got the user input from here. We composed the email here, and we sent the email here. So once we're done sending the email, we end it. We end the process. So that is what these default nodes do. Start node, helps you to point at the very first node that should be run, and end node helps you to terminate the operation of the graph. Now, for every node you create, for every Python function or JavaScript function that you create as a node, you actually have to add it to your graph. So when you set up your graph, something like builder, all caps, nope. You say builder equals state graph, and you pass in your graph state, or let's just say state. So you pass in your state to state graph, so you have your graph builder. Now inside your graph builder, once you have defined your node, you have to add it to this graph builder. You have to add it to this graph. So you say builder, and you call the add node function. The add node function, that's the function that you use to add nodes to your graph. So you say add node, and then you give it the name of your node and the function. You give it the name of your node and the Python or JavaScript function. So let's say we call this my node. So you give it the name of your node, that's the name you want to call your node, and you also pass in the name of the function. You just pass in the name of the function. So if the function is, let's say, send email, if the function is send email, you come here and say send email. Send email. Now, it is best practice to always give your nodes the name, a name rather, that describes what they do. A name that describes what they do. So if your node sends mail, call it send mail. If your node drafts mail, call it draft mail. And sometimes also, a lot of people just try to match it with the name of the function. And that's why in LangGraph, if you just pass in the function, let's say you don't pass in the name, if you just pass in the function, it will automatically give the node the name of the function. So if I define a send mail function, that is to be my node, and I pass it to this add node function directly, send mail is going to be automatically be the name of my node. So that's what I will use to reference it when I'm connecting edges or when I'm doing anything with the node or using it in the command feature that we're going to be looking at later. So yeah, this is how you we've talked about what nodes are, how you build them, the arguments they take, how you add them to your graph. Now let us go into VS Code and actually see LangGraph nodes in action. So now that we understand what nodes are and their purpose in LangGraph, let us write some node code. So here in VS Code, first I'm going to create a new file. I'm just going to call it nodes.py. Or let's just say nodesdemo.py. I should start adding demo to always suffix all my files with demo now. So nodes demo. And what we're going to be doing in this demo is that we're going to be creating 3 nodes. A graph that has 3 nodes. Now, one node is going to take the state, just the state of the graph. Another node is going to take state and a runnable config for configuration. And our third node is going to take state also, but also take a runtime context. So we're going to see how we can work with all these arguments that our nodes can take. So to begin, first let us import our dependencies. I'm going to say from typing, import. And then we're going to import from here, we're going to import typedict. And we're also going to import, I think just typedict from here. Then we'll say from LangGraph.graph, we import stateGraph. And we also import our default nodes, the start node and the end node. Start and end. That's good. Now the next thing we're going to do, we're going to define the state for our graph, our state schema for our graph. So say class, nope, all caps on. Class, let's call it graph state. Taking typedict. And we're just going to be defining 2 state variables, our input and our output. Our input and our output. I'll call output result. So we're just going to have an input which will be of type string, and we have results which will also be string. So input, which is user input, and result, which is what we want to send back. Now, the next thing we're going to do, we're also going to create our context schema. Yeah, we're going to be creating our context schema. And our context schema is going to just be a place where we're just going to store some static values that we can use within our graph. We don't want them to change. We just want to use it within our graph. But like I said, there's another video coming up on context schema, so you don't need to try and fully understand what this does from this video. So for that, I'm just going to create a class and call it context schema. This will also just, oh, I mistakenly opened another shell. Yeah, this will also just take in type dict. And what can we store here? Let's say user ID. Let's say user ID for our user, and that will be a string. So there we have it, our context schema, something simple. We don't need to go wild with that. Now, the next thing we're going to do, let me close out from this. Next thing we're going to do is to create our nodes. So first, I said we're going to create a node that only takes in state. A node that only takes in state. So I'm going to say define plain node. It's going to take the state argument, and we're going to pass in graph state for this. And that'll be good. Inside that node, we're simply going to just print executing plain node. Executing plain node. So that we can know the node that we're in. Just going to put them dot 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 here. So executing plain node, and let us return an update to the state. So I'm just going to return an update to results. And let's just greet and say hello. Let's assume that the input is going to be our name. So I'm going to say hello, and I'm going to say state input. So yeah, that's going to be our result from here. And that's everything we need to do here. That's everything we need to do here. Now the next node that we're going to create is the one that takes in a config, a runnable config. So I'm going to say define node with config. First, we pass in our state, which is still going to be done the same way. Then we can pass in the config argument, and that config will be of the type runnable config. Runnable config. And because we have runnable config here, we need to import it. So say from lang chain call runnables import runnable config. Runnable config. So we have our runnable config, and thus we have a configuration. We have passed in a configuration to this node. Now for this also, I'm going to put a print statement and say executing node with config. Executing node with config. Now let us try and get one of our configuration properties, from the runnable config object. Now for that, I'm just going to get a thread ID. And say config.get from configurable. If you cannot access configurable, just give us an empty dictionary. And inside configurable, we need you to help us get a thread ID. So yeah, we can just print out the thread ID. Say print f, and just do this dub, yeah, and say accessed thread ID from config. I'll just pass in our thread ID here. And we can just return something back to state. Our results. That will be config successfully accessed. So this is a node with a config object, a runnable config. And we decided to use one of our configurable fields, which is thread ID. So we can set a thread ID on this upon invocation. So we have the node that takes a config. The third node that we're going to be creating is the node that is going to take in a context schema. So once we define that, I will say node with runtime. Node with runtime. First to pass in the state, which will be graph state. I'm just going to copy that from here. Graph state. Good. Then we have runtime. That is the argument that takes in the runtime context. So right with runtime, and like I said, it will be a runtime object. A runtime object. And we need to get that runtime object from LangGraph. You can get that from LangGraph. From LangGraph.runtime import runtime. So from LangGraph runtime, we get runtime, and we need to annotate this with the schema that we define for our context. So I'm just going to grab that from here, context schema, and put it here. So that's good. Let's go into our node function. And what do we do inside here? First, let us print out our typical message that shows that we are executing this particular node. This will be node with runtime. And next, what do we do? Let's just get something from our runtime context. Let's just get that user ID. So for that, I'm just going to say user ID equals runtime.context.user ID. Runtime.context.user ID. I think we need to access this as a, not this way. Sorry. Yeah, user ID. So runtime context user ID. So now that we have it as this, I'm just going to copy this print statement also and come down here. And I'll say access user ID from runtime, from the runtime. Yeah, from the runtime, I'm going to give this user ID. So that's good. Later on, I will see if I can access my user ID this way. But can I? I don't think so. Okay, so we have our 3 nodes. And now we can start building out our graph. So I'm just going to collapse this 3 for now so that I can get some room. At the start, I'm going to say builder equals state graph. And the first thing we'll pass to our state graph is our graph state. So let's get graph state. That's our graph state schema. Pass it in. Now, because this has a runtime, context, we also need to pass another argument, which is going to be context schema. Pass context schema, and that will be set to our context schema, which is schema we define for our context. So pass those 2 in. That's all good. Getting an error here. Oh, okay. Just set this equal. Yeah, sorry about that. So equal. So state schema, context schema. Yeah, we get context schema. And now we can start adding our nodes. So I'm going to say builder dot add node. And our first node is a plain node. So first I'm going to put in the name of the node and the function of the node. Name of the node and function of the node. And that's the same thing we're going to do for all our nodes. So I'm just going to copy this and duplicate it twice. So we have node with config and node with runtime. And now we have all our nodes complete. We've added all our nodes, but we need to connect them. We need to build a workflow with our nodes. And what we want to do is that we want to go to the plain node first. Then after the plain node, we want to go to the node with config. And after that, we want to go with the node with runtime. And after the node with runtime, after running that operation, we want to terminate the entire graph workflow. Now to do that, we need edges. So let us start adding edges. And going to say builder.add edge. And like I said, to tell LangGraph the node we want to start from, you have to use the start node. So the start node will be able to point at any of your defined nodes and say, this is the node that is going to serve as the entry point. So we start with start node, and we say go from start node to plain node. From start node to plain node. Then after that, we want to go from plain node to our node with config. Then from our node with config, we would like to go to our node with runtime. And after we're done in our node with runtime, we want to terminate the operation. So we go to our end node. That's our workflow. Start, plain node to node with config to node with runtime, then node with runtime, terminate. Awesome. Now we can simply come down here and compile. So I'm going to say graph equals builder.compile. Awesome. And now we can run our graph. Just put a comment here and say run graph. Run the graph. And for the state, or rather, we need to define an initial state. So I'm going to say initial state. And all we're going to do here is just pass in an input. And because we simply want to say hello, here, I'm just going to pass in my name. Pass in my name as the input. And this is going to be passed in as the input argument for our invoke function. But remember, our graph also takes in a configurable or a runnable config for configuration, and also takes in a runtime context. So we need to define values for that too, so that we can pass it into our invoke function. So let us do that. First, let us start with the configuration. I'm going to say run config. And we're just simply going to use a dictionary where we set a configurable and set that to a thread ID. And this thread ID, I'm just going to make it up and say ABC123. But this is a very good way for you to track your node operations. But here I'm just going to use a fictitious value. So we have that, and also we want to define a context. Let's say graph context. Yeah, graph context. And the only thing that we defined in our context schema is just user ID. So let's say you want to track a user ID for this, or you need user ID information within your graph workflows. You can also set it here. So I'm just going to say user ID. I'm going to set that to Optimus Prime. Optimus 103 Prime. Okay, so that's our graph context. And now let us invoke our graph. I'm going to say the final state equals graph.invoke. Graph.invoke, and here we'll pass in for our state. In some of the examples, we've just been dumping our state in directly into our invoke brackets, that's the parentheses. That's what you do when you just want to pass in state. You don't want to pass in any other argument. But when you want to pass in state and other arguments, you have to use the input argument to pass in your state. So we say input, and we pass in the initial state for this. Next, we want to pass in the config, which is going to be done with the config argument. So for this, we pass run config. And finally, for our context, we use the context argument, and we pass in graph context. That's good. So we have our input, we have our configuration, and we have our context. Now let us see what the final state looks like and all the print statements we're going to get from running all our nodes. So I'm just going to say print final state. And just below that, we're going to print our final state variable. Final state. And now let us pull up our command line. Been typing a lot since. Pull up our command line. And we're just going to run Python. Oh, I'm not in my environment. Yeah. Let me activate my virtual environment. That will make everything blow up in my face if I don't. So bin activate. Good. So now we're in our virtual environment, and now I can run Python nodes demo, Python nodes demo.py. Let's run that. So we get executing plain node, executing node with config, and it was able to get our thread ID, which is ABC124. Then executing node with runtime, which is our third node, and it was able to access our user ID, which is Optimus103 prime. And the final state says the input is my name, which I passed in, and the results are config successfully accessed. Config successfully accessed. Now this says config successfully accessed because if we go, if we just go down, let's pull it down. We didn't return state from our runtime. I don't think we didn't do that. So it just automatically returned the state. Just automatically returned it. But normally we're supposed to return a state. You can just return the entire state. Yeah, you can just return the entire state if we don't want to change anything. So everything is still going to work fine if we do that. If I clear the screen, let's clear this. Just run that once again. Everything still works fine. Everything still works fine. So we've been able to see how nodes work, how we can return objects to state, and if we don't want to change anything, it kind of returns it by default, but we cannot, or we can also be explicit about that and just return the entire state object, and everything is going to stay the same. And we've also seen how we can pass in state to our node. We've seen how we can pass in a configuration object with runnable config, and also use runtime context, which I said we're going to be dedicating another video to. In this video, we're going to be looking at another very important component of LangGraph's Graph API, and that is edges. LangGraph Graph API edges. Now, we've looked at nodes, and we describe nodes as the processing units in your graph. They are the main action points. They are the action takers. Now, what are edges? Edges define the flow of your workflow. They are your routing logic. They are how you move from one node to another, and you can move directly or you can move conditionally, as we're going to be seeing very, very soon. So like I said, edges determine the workflow. They determine when to start the graph, they determine when to stop the graph, and they basically manage the sequence of communication between your nodes. So edges, let us represent them as arrows. Let's say they're arrows. So if you need to move from this node to this node, you add an edge. Yeah, this is what an edge is. That's the mental model. So I want to go from this node. Let's use an email example. We want to get user input for an email. Then we want to draft the email. I want to send the email. So let's say here we get user input. Here is where we draft the email, and here is where we send the email. So this is the action we want to do first. Then we want to perform this action, then this action. So we have to first tell our graph to start from this node. We have to tell it to start from this node. So for that, definitely we will need our start node, which is the node that determines or points to where to start from. And for us to use this start node to tell our graph to start at this very node that takes user input, we need an edge. We need to connect an edge. So we need to say, go from here to here. So we go from here, we take user input. Then the next thing we want to use that user input to compose our email. We want to compose our email. So we need to tell it to move from this node to this node. And we also use an edge. And when we are done drafting the email, we also want to send the email. So what do? We take another edge and we say go from here to here. Go from here to here. And when we're done with all the operations, when we're done with our graph, we can simply go to our end node. And how do we go to our end node? We also use an edge rather. We also use an edge to go to our end node. Yeah, I put 5 here for some reason. This is not 5, this is end. Let me correct that. Okay, so we go to our end node. So you see, our edges are our routing logic. If nodes are our action takers, then edges are our orchestrators. They're the ones that says this is the next thing to do, then this is the next thing to do, then this is the next thing to do. And it can also say these are the next couple of things to do. As we'll be seeing later when we start working with parallel workflows. But basically, as you can see, our edges, we use them to go from one node to another. We use them to define our routing logic. Now, there are two types of edges. What we are currently seeing is what we call a normal edge. Let me just put that here. Come back. Normal edge. Normal edges. So they are direct. They basically just go from one point to another point. And they are defined explicitly. Go from this place to that place. From point A to point B. Now, aside a normal edge, we also have conditional edges. Now, with conditional edges, we can dynamically move to nodes. So based on a condition, we can say, oh yeah, if email body is empty, go to this node that requests for a body of the email. But if the body of the email is not empty, that means we have the email we want to send, then go to this node that sends the email. So we can do conditional, we can have a conditional logic with how we route to our nodes. Now, there's also, LangGraph also kind of separate out some edges as conditional entry edge and normal entry point edge, but everything is still just normal edge and conditional edge. It's either it is straightforward or it is conditional. That is still the whole gist of everything. So these are the two types of edges that we have in LangGraph. And based on your operation, if you know if your workflow is defined, if you know that you want to just go from this node to the next node, use a normal edge, use a direct edge. But if you need to check a particular condition to know which node to go to, you can even be between 4 different nodes. You want to determine which node to go to between 4 different nodes. You can use conditions to conditional edges rather to route to the node based to a node based on a condition. Now, before we go to VS Code to check out how we can work with edges, to add an edge, you simply use the add edge function. So when you set up your builder using StateGraph, you can then say builder.addEdge. Builder.addEdge. Let me bring this down. Then bring this here. Yeah. So add edge, and in add edge, you use add edge to add normal edges. Yeah, use them to add normal edges. So you simply say go from this node, let's say node A, and from there go to the next node, which let's say is node B. So that's how you add a normal edge. So this is how you add a normal edge. Now, adding the conditional edge is a bit different. Now, a conditional edge is defined with a function. Let me just get a new box for that. Let's get a new text box for that. Meanwhile, let us shift this to the side. Get another box for that. Yeah. So to add a conditional edge, you say builder.add conditional edges. Add conditional edges. Now, the first thing that goes into here is the node that you want to route from, the node you're currently in. So let's say node A. Then the next argument that goes into this is a function, a routing function, a pure Python function that can take in state. That function can also take in state in case you need some state variables to determine the parameter you want to use to check your conditional logic. You want to use to run your conditional logic rather to know the next node to go to. So we have a routing function here. And that function is going to return the string name of the node you want to go to based on the condition. So you can say if let's say if 5 is less than 10, then go to node B. You return node B as a string. Or go to node C. You will return node C as a string. So you basically return the string name of the node that you want to route to. If you want to do parallelism also, you can return a list of nodes, so it will just route in parallel to those nodes. And yeah, and if you want to, sometimes if you don't want to return the node in the function itself, if it's just a pure function that returns true or false, you can add a dictionary here. The dictionary is going to take two properties. One is true, Boolean, and the other is false. So here you can say, let me close this dictionary. Here you can say, if the condition in this routing function is true, that's whatever you return. Now you have to return a Boolean from your routing function. If you're going to use this style, you have to return a Boolean from your routing function. And you can say, if true, then go to node B. Let me just put B here so I can say space. If true, go to node B. And if false, go to node C. So this is another signature. This is another syntax for add conditional edges. So you can either do it this way, where you return a Boolean from your routing function, and if it is true, it goes to this node. If it is false, it goes to this node. Or you can just say, you know what, I'm going to return the node from my routing function. I'm going to return a string value from my routing function, which is the name of the node I want to route to next. So yeah, that's how you add conditional edges. Let us edit to VS Code and see how we can work with edges. So now that we understand what edges are and how they work, let us write some edge code. Back in VS Code, I'm going to create a new file and call that edges-demo.py. Now, in this demo, we're going to be creating 4 nodes. We're going to have a graph that has 4 nodes. And let's just assume they are node A, B, and C. Node A, B, C, and D. Those are our 4 nodes. Now, what we're going to be doing is that we're going to directly go from node A to node B with an edge. Then we're going to conditionally go to node C or node D using a conditional edge. So we're going to be able to see normal edges and conditional edges in action. Let's get started. First, let us bring in our dependencies. I'm going to say from typing. Let us bring in typed dict. Okay. And we're going to go into LangGraph and and bring in our graph tools. So state graph, start and end. So that's good. Now the first thing we're going to do is create our class. That's the first thing we do. So let us create graph state. Let's pass in typed dict. And here we're going to simply have 2 state variables. The first one is going to be input, which is for user input, and the next one is going to be something called execution part, which is basically going to be a list, and that list is going to have the nodes that we hopped through. So it's just going to show us how we executed, whether we went for A, B to C or A, B to D. So let's do that. Let's say input string and execution part, and that's going to be a list of strings. Yeah, so those are our 2 state variables, and now we can start creating our nodes. Now first I will do node A. I'm just going to call it node A, just call them node A, B, C. So this is going to take in states, graph state. And yeah, that's all it needs to take in. It will return a dictionary. You can explicitly say that, or you just allow LangGraph to do that for you. Then yeah, we're going to put a statement to say executing node A. And what we're basically going to do here is that we're going to add this hop into our execution part. So I'm going to say new part equals state. No, let's not do this. Yeah, state dot get execution part. Get the execution part. If it's not available, we'll just use we'll set it to an empty list. And we tell it that we just want to tack on node A as our first hop. We tack on node A, and since we are setting a new execution part, we're just going to update the state and say execution part, and that will be set to our new part. So it adds node A to the list, and that is good. So we have our node, it just pays printing, executing node A, then we add node A to the execution part. I'll just return that update to our state. Now, what every node is going to be doing in this demo is basically the same thing. They're just going to add to the execution part that, yeah, I was here, I was executed, I was here, I was executed. So I'm just going to take this function and create 3 other versions of it. So say node B, this will be node B, any other, yeah, node B, yeah. So yeah, just say node B. Then come down again, and this will be node C, okay. So, and lastly we have D. So let us do the update once again. D. So we have node A, B, C, and D, and what they do is just add themselves to the execution part. So I'm just going to collapse all that. And like I said, what we want to do is that we want to route from A to B directly. So that's a normal edge. But from B, we want to dynamically route to either C or D. From B, we're going to dynamically route to either C or D. So let us write the code that is going to do that for us. Now, like I said, a conditional edge is a function. A conditional edge is a function, so we have to define it as a function. So I'm going to call it should continue. Should continue. And like I said, it can take the state, because we'll definitely need something in the state to run our conditional logic. And let us say we can actually instruct it from our input. So from our input, we can tell it, oh, go this way or go that way. So let us then say if from our input, from anything the user types into our input, we get go to C. We get go to C in state input. So if there's go to C in state input, then we want to return node C. Else, we'll simply return node D. So basically, we have a function that checks whether we have go to C in our input, and if we do, it's going to return node C. If not, it's going to return node D. Let's just put some print statements around there just to show some execution part. So I'm going to say print evaluating conditional edge. Evaluating conditional edge. Then here we'll say print continuing to C, and here we'll just say continuing to D. Continuing to D. So that should be enough. This is the function, this is the conditional function that is going to run when we are adding our conditional edge. So now that we have this, let us start setting up our edges using the add edge function. First, we need to build the graph. So I'm going to say builder equals state graph. And we're going to put in our graph state. Graph state. Next, let us add all our nodes. Now I'm going to be adding them as node A, node B, node C. So I'm just going to say add node and pass in the functions themselves. So node A, this node, the name will automatically be node A. And I'm going to do the same thing for nodes B, C, and D. So B, C and D. So we have all our nodes added. Now let us add our edges. Let's add our edges. Now, like I said, we want to go directly from A to B, then conditionally from B to either C or D. So first we want to go from, we first want to kick off our graph. So we first need to add the edge. That will be using add edge. We need to first go from the start node, that is the entry point node, the start node, to node A. So this tells our graph to start from node A. So we start, then we add another add edge function. And here we want to say, go from A directly to B. Go from A directly to B. Now, this is a normal edge. This is also a normal edge. These two are normal edges. They explicitly define the node to go to. Just say, go to this node. It's direct. Now, once we are at B, we want to conditionally go to C or D. So, in this case, we have to say add conditional edges. Add conditional edges. And where are we coming from? Or where are we currently at? We are at B. And then the next thing we put is our routing function. Should continue. And inside should continue, we've already set the logic that if there's go to C inside our input, it should go to C. If not, it should just go to D. So we have that in place. And at the end of the day, in our final state, our execution part is going to show us how this played out. So we have added our edges. And now we can, to terminate the graph, we'll add both C and D to end. So once node C is done, end, that's if we go to C. And if we decide to go to D also, once it's done, it can simply end. So that's all good. We have all our edges set up. And now we can build our graph. So graph equals builder.compile. And now we have a graph that we can test out. So I'm going to say test the graph. Test the graph. So how do we test this graph? Definitely we test it by passing an input. So in the first, let's say in the first example, we don't want to mention that we're going to C. So I'm going to say initial state 1. We set an input. And inside our input, we just say hello LangGraph is awesome. Hello LangGraph is awesome. These are our initial state. And you can see inside this input, there's nothing like go to C. There's nothing like go to C, which is what we're looking for here. There's nothing like go to C. Let's come down, and here we can say final state 1 equals graph.invoke. We pass in initial state 1. And here we can print final state 1. Can print final state 1 so that we can see what our final state looks like. And we're going to check the execution part to see how this graph flowed. Let's save this. Now let us pull up our command line. Clear it. Then we run the function Python edges demo.py. Hope we don't have any issues. Let's hit enter, and bam. So here we have executing node A. So we hit node A, executing node B, we hit node B, then we got to the conditional edge, and it continued to D, and it said executing node D. So there was no go to C in our input, and as you can see, the execution part says node A, node B, and node D. No node C. Node A, node B, and node C. Now, let's say we change that. Let's say we switch things up. Let me clear this. And we just say hello, go to C to continue. Hello, go to C to continue. Let's try this out. Let's see what we get from this. Pull this up. On the file once again. And now we see executing node A, executing node B, evaluating conditional edge, then continuing to C. And it says executing node C. And if we look at our execution part, we see node A, node B, and node C next. So it decided to go to node C instead of node D. Awesome. Simply awesome. So in this video, you've seen how to work with edges, and you've seen how to define a normal edge, and also how to define a dynamic edge using the conditional edges in LangGraph. So in this video, we're going to be looking at the runtime context, the LangGraph graph runtime context. Now, sometimes there are some values you don't want to specify in your state. Most likely probably because the values don't change, or they are like configuration values or just static values that you will need to work within your graph, but they're not state values that will most likely be changing from one node hop to another. Things like probably your LLM provider, a file URL, a database connection, even prompts. You want to just store them throughout anytime you run your graph. They're not going to change. You can override them for specific runs, but they mostly don't change, and they are not involved in the actual state activities, but you still want them to be present for the graph to access. Probably things like user ID, stuff like that. You just want to hold them somewhere so that they can be available for your graphs to use. Those are the type of things you keep in your runtime context. They are basically the candidate for configuring your graphs in LangGraph. They're the favored candidates for configuring your graph over runnable config based on what I saw in the new documentation, the 1.0 documentation of LangGraph that is going to be released this October. So these values, you provide them at runtime. They cannot be modified by your node. In fact, they can't be modified. They can only be changed at your invocation. Anytime you invoke your graph, that's the only time that you can override them or set values for them. But your nodes can't change them. Your nodes can't change these values. Also, you can set defaults for them at the beginning of when you're setting up their schema, because you also need to set up a schema for this data bucket. When setting up the schema, you can provide default values. So that you don't have to always provide all the values when you want to invoke. When you want to invoke, you probably only provide values you want to override. And if you have no value you want to override, you don't need to specify them. So let's say you have a graph. And let me make this yellow. Okay, or pink. Yeah. Let's say you have your graph. So you have your state already operating in your graph. And let me make this solid. So let's say this is your state. But you want to have some values available in your graph that are not going to change, that the state is not going to change. So that's what you introduce a runtime context for. So you store these values in your runtime context, and your graph can always pick them up anytime it needs to access them. Like I said, things like probably a file URL, some database pointers, a list or an enum list that you just want to use within your operations. You can just keep them in this runtime context. And like I said, you set default values for them. Things like your LLM provider and stuff like that, you can always set default values. For example, let's say you are using OpenAI, so you just set your LLM provider to be OpenAI. You can also set the name of the model you want to use, whether GPT-4o, O1 mini or stuff like that. You can set that. But at runtime, anytime you want to invoke the graph, you also have the ability to override those defaults. Now, how do you define this? How do you set this up? Let me move this down. Now move everything down. Okay, good. Let's move everything down. Now, you first have to define a schema. Just the same way you do with your state, you have to define a schema for your context, your runtime context. So say class, let's say context schema. but you can give this any name you want. Basically, it's recommended that you use a data class. And that makes sense because you will be setting default values. If you use a typed dict, you can't set default values. So that's why typed dicts are mostly used for state, because most of the time in state you don't want to set default values. You just want to have an initial state when you run your graph. But for context schema, you would be setting default values a lot, so it's better you use a data class so that you can go into that data class. Let me put it a little bit. Go into that data class and define values. Let's say user ID, which is a string, and you can set that string to Optimus 001 prime. So you can set that right there in the schema, and if you don't override it when you are invoking your graph, this is just what your graph will continue to use anytime it needs to access this data. So once you have that, once you set your context schema, you then need to pass it to your when you initialize your graph with state graph, you need to pass it to state graph. So you say builder, let me increase this a little bit. Okay, let's go to large. Okay, good. This large. Okay. So when you say builder, state graph, so obviously you want to pass your state schema first to, let's say, graph state. But then you need to pass a context schema. You need to pass this context schema. If you want to use runtime context, you need to pass the context schema, and that's going to be set to your context schema class. Going to be set to your context schema class. Bring that in. Then I can't color this guys individually. Yeah, so that's kind of a bummer. So what did I do? Back to black. Okay, so you pass in context schema and you pass in your context schema class. So you pass it in, so the graph is aware that you want to use context schema. And then once you have this set up, you can then have access to your context schema inside your nodes. So let's say you define a node, say my node. The first argument will be your state, definitely. So that will be your state class. And the next is going to be runtime. It's going to be runtime. And this is going to be of type runtime, which you will get from LangGraph.runtime. We're going to be seeing it in the demo that we'll do after this whiteboard session. But you need to annotate this runtime with your context schema. You need to annotate it with your context schema. So with that, you have your runtime available inside your node. And if you want to access it, let's say we want to access our user ID, you can say something like user ID equals runtime.context. So runtime.context, context.user ID. Because it's a class, you can use the dot notation, runtime.context.user ID. That's how you get the values in your runtime context inside your nodes, and you can use them for anything you want. You can use them for any operation that you need to perform in your node. For example, let's imagine that email example. Let's say in the context we already have the name of the user, or a dictionary that contains the name of the user is already in the context. So when the input comes in as the body of the email, and we go to the node that drafts the email, it would automatically put the user's email and the user's name in the from field, and also personalize the email with the user's name. And yeah, everything is gotten from the context. All those information are gotten from the context. And when it goes to another node, it can also perform any operation with the user's information. So those are the benefits of using context. It just gives you all these values that you can store in the background, and you can just pick anytime you want. But like I said, you can't change them. You can't change them inside your nodes. You can only change them at runtime. And speaking of runtime, whenever you want to override, let's get another box now. Let me push this down. Let's bring this down. Let's put this two up here. So whenever you want to invoke your graph, and you need to override any one of your context properties. First, you need to make sure that you're passing your state as input. You can't just pass it directly because you need to be able to use another argument. And the argument for passing in context is the context argument. And let's say we want to override the user ID. We simply just pass in another user ID. Let's say for this particular invocation, we want to use another user ID. You can pass in another user ID and say user USR123. Yeah. And that will override the first user ID, which is Optimus Prime, Optimus 001 Prime. It's going to override that for this particular graph invocation. So that's how you can override the defaults that you have defined inside your context schema. So that is runtime context, and the next thing we're going to be doing is going into VS Code to see how this works. So back in VS Code, let us run a simple demo that is going to show us how the runtime context works in LangGraph. To begin, I'm going to create a new file, and I'm just going to call that runtime-context demo.py. Okay, that's good. Now it's going to be a simple, straightforward example. We're simply going to be storing some information in our runtime context. We're going to be invoking without overriding, then we're going to be invoking with overriding. So yeah, that's the old gist. Let's begin. First, let us bring in our data class. Say from data classes, import data class, because that's what we're going to use to create our runtime context. Then we bring in typed dict for our state schema itself. Then we're going to bring in our graphing tools from LangGraph.graph. And finally, we're going to bring in runtime. So runtime is from LangGraph.runtime. Bring in the runtime class, runtime. Okay, so that was all good. Let's start by creating our state schema. So the typed dict, and we're just going to have an input to be a string, and we will have a result which will also be a string. So user input and whatever we want the result to be. We are more concerned about our context, runtime context. So yeah, just put something there. Now for our runtime context, as I said, because we want defaults, we're going to use a data class. So the data class, and then we can say class, and we call this my graph context. My graph context. Like I said, you can give it any name you want, call it any class name you want. So just get very descriptive. Now the first thing we want to put here, let's put a property called user agent to track the user agent that is in operation. So user agent is a string. Then we also want the URL to the official LangChain documentation for some reason. By the way, I'm not trying to build any specific thing here. I'm just trying to dump data to just show how runtime context works. So just going to be doing random stuff. So let's say for some reason we want the documentation URL for LangChain. So let's say it's at docs.langchain.com. And for some reason, there is a DB connection that we need to maintain because we might want to call our database. So I'm just going to say DB connection, that's a string, and set that to MySQL, user :password, and it will be at localhost. So we're running the local DB and the MySQL port 3306 / the name of my database, which is my DB. So yeah, let's say these are the information we want to keep in context: the user agent, documentation URL for LangChain, and a DB connection. So we have this. Now let us define a node that is aware of our context, and it accesses our context and just prints a bunch of those stuff out. So let us do that. Let's say define node with or let's say context access node. Yeah, and like I said, as usual, your node is going to take your state, but then it can also take the runtime. The runtime argument that is set to runtime type and is annotated with your runtime context schema. So we'll get that in place. And inside here, I'm just going to print executing node. And inside here, what we're going to do, we're going to get all those context information. So let's say user agent. Or first, let us get our DB string. So DB string equals runtime.context.db connection. Then we can also get our documentation URL, say docs URL, runtime.context.docs URL, and finally we get our user agent. Awesome. Then down here we can simply print 3 of them. So first, let us say current DB string, and we'll just give you the DB database string. Go down and say documentation URL. That'll be docs URL. And lastly, we can say print user agent. And that will be in a user agent, your user agent variable, rather. And just for good measure, let us return something to the state. Just going to return results. And we'll say context. This is an F string. Context accessed. And the DB we're using, let's say the DB we're using. Context accessed. The DB we're using is let's just print a subset of, let's put a substring of the DB, because later on I'm going to be switching it from MySQL to Postgres. So this will just tell us when it has switched. So we only need we need DB string, and we call the split function. Now let us split it by the 2 double slash and get the very first part of that string. After that, we can just say dub. So that when we switch to Postgres, it will just tell us the Postgres part. So yeah, we have this. So this is the node that is going to be accessing our context. And with this in place, we can just quickly build out our graph as a single node graph. So I'm going to say builder equals state graph. Now, like I said, we're going to give state graph our graph state as we always do. Graph state as we always do. But now, because we are using context schema, we also have to make our graph aware that we have a runtime context. So, and that will be done using the context schema argument, and then you give it the schema that was defined using the data class. So give it that schema class, and we can go down here and then say builder.add node. We only have this context access node that we defined, so we just put it here. Then let us add our edges. Builder.add edge. We start and go to our context access node. Then from there, From there, we just end. Yeah. From there, we just end the graph. And finally, we can compile our graph. Graph equals builder dot compile. Awesome. So we have a simple one node graph that we're just going to use to test our runtime context. So let us try out some things. First, let's run it without any overriding of the default. So I'm going to say initial state, just say initial state equals is that spelled? Okay. Initial state. So that will be input. And here we can just simply say anything. Let's say start process. Just call it start process. And we can just feed that. We can just invoke that and say final state. Final state equals graph dot invoke initial state. Graph dot invoke initial state. And down here we can print our final state. Print our final state like this. Okay. So, like I said, for this first run, we're not overriding anything. We just want to use the default inside the context runtime or inside the runtime context. So let's save this. Drop the command line. Now let's run the function Python runtime context demo.py. And let's hope everything works fine. So we actually get an error, and this says non-type object has no attribute DB connection. Now this might cause us to kind of look inside here and feel we do have a DB connection. Like we do have a DB connection here. So why don't we have that? But then I remember that for runtime context, any field that we define in our class that we don't set a default value for, we need to provide it. We need to provide it when we are invoking, because that value cannot stay empty. So here we are simply just passing in the state. So we're not setting the context. We're not giving this user ID a value. So it doesn't have a value. So it needs a value to operate. So let us fix that. Because we want to pass context this time, we need to set input equals initial state, and then we then pass in context. I didn't want to pass it at first because we're not overriding anything, so I felt okay, let's just pass in the state and let's see what happens. But then we have a field inside our context schema that doesn't have a default, so we have to set a default for that. So let me just set that. So user agent. So I want to fix that first. If we still get an error, we're going to figure it out. But for now, user agent, let's call it default platform. Default platform. Let's say that's the name of this platform for some reason. So yeah, let's pull this up. Let me clear the command line. And now let us run this again. And yeah, that turns out that was the issue. Turns out that was the issue. But it's sometimes some issues arise, and it's kind of good that it came up because I forgot to mention that part, that if you don't set a default for a field in your context schema class, it's going to be a required field. That automatically makes it a required field. So you need to define it in your context. So this runs fine. We are able to print out our current DB, our documentation URL, and our user agent. We're not overriding any of the defaults for now. We're just simply setting the user agent, which is a required context value. But let's see if we can override the database connection. So let's say here, we say for this run, I want you to override DB connection. Now, passing in a value for a required value is fine. It is not overriding anything. Passing in a value for a field that has a default value already, you are overriding that default value. So that's what we're doing for DB connection here. So let's say for this, we now decide to go with Postgres, new user at remote host colon 5, what's Postgres 5432, right? Yeah, 5432 / production. So let's say this wants to switch to our production database, and our production database is Postgres, and the name is production. So let's say this, and now let's pull up our command line. Let's clear, and let us run this file once again. Boom. Now the current DB string has changed to Postgres. But now if you look at the input, or rather in the final state, you see our result now says context accessed DB, and the DB is Postgres. Before we had MySQL, now it's giving us Postgres. So you see, we've been able to use runtime context. We've also been able to access it, and you can use it for anything. You can use it for anything. You can use it to call APIs. For example, you might also want to store API endpoints there, so that when you want to call an API, you just pull the URL from the context and use it to call the API that you want to call. And I said I wanted to test something out, which is the fact that in our edges video, we're able to, no, in our nodes video rather, we're able to access runtime context like this. And I believe that's because we're using a typed dictionary. But using a data class, we most likely, I don't think we'll be able to access it this way. But let's try. So save that, run. And yeah, definitely we get an error, because this is a class, not a dictionary. This is a class, not a dictionary. So if you use a dictionary like type dict to define your context, you won't be able to set default, which is one thing you have to note. You won't be able to set default. That's why data class is chosen. So just use data class. And if you use data class, it's a class, so you need to use the dot notation to get your fields. So yeah, just wanted to put that out there also. So in this video, we're going to be looking at the send feature in LangGraph. Send. Now, send is used to perform map reduce operations in your graph workflows, but it would make more sense using an example. So let us assume that you have a node. And this node generates a bunch of student scores. So you have, let's say, like a dictionary inside them, or a list of dictionary objects containing scores for each student. Let me expand this. So inside here, let's say you have Mike, and Mike has scored 60. Then you have another dictionary, let's say Monica, and Monica scored 80. Then you have okay, get this down. Okay, let's do this. Then you have Juan, who got 90. Okay, so you have a dictionary of student scores. And these are generated by this node. This node just generates them or pulls them from the database. So let's just use that. Let's say this node pulls them from the database. And sometimes this database will contain 5 students, sometimes it contains 10 students, and sometimes it contains 50 students based on the class. Let's say you're going from class to class. So let's say in class A, there are like 50 students. In class B, there's 40 students. In class C, there's 70 students. So The number of students, you can't determine it. It's not fixed. The number of students is not fixed. So this graph has to work on different tables for each class. So each class has those student scores in each table. And like I said, one table can contain 50 students or 50 rows, and that table of scores can contain 40 students. So you don't know the number of scores you'll be getting beforehand. But then you have another node that needs to process these scores. You have another node that needs to process these scores. So what the node does is that it takes a student score. The node takes a student score, then calculates their grade. It calculates their grade. So let's call this node calculate grade. Calculates their grade. So let's say anything above 70 is an A. From 50 to 60 is a B. From 40 to 50 is a C. Whatever grading system you want, this node calculates it. And what you want to do, you want to go from this node that gets all the students from the database and go to this node that calculates the grades. But this node can only calculate the grade of one student. So you need to run multiple of it. But you don't even know how many you have to run beforehand. You don't know because like I said, a class has 40 students, another class has 50 students, another class has 90 students. So you don't know beforehand how many students are in a class. So because of this, you need to use map reduce. You need to use map reduce, meaning that you need to be able to spin up as many instances of this node for each student. You need to be able to spin up as many instances of this node for each student. But you don't know the number of students beforehand. And once you're done calculating the grade of each student, you have to prepare it. That's using another node. You have to prepare it in a final report. So let's say this grade is this node is final report. So you need to prepare it in a final report, and you need to combine all the results from all these nodes. So like I said, you need different instances of this node. You need multiple instances of these nodes according to the number of students that come from each table. And at the end of the day, you need to synthesize all this information into here. So what send allows you to do, what you can do with send is that when this node fetches those users, or rather when it fetches those student scores, depending on the number of student scores, you can then use them to generate multiple instances of this node. You can use send to generate multiple instances of this node. Go here, another one. So you generate those multiple instances based on the number of scores you get. And also, they would work on different states. Each of them will work on different states. This will work with Mike. It will work with the Mike object. This will work with the Monica object. This will work with the Juan object, and more and more and more. Dilip, Kwaresh, more and more names that come up. It is going to spin up a node for each of those records. It's going to spin them up for each of those records. So the fetching of the records, you don't know the number of records you fetch, but when you fetch those records, you can then use send to loop over that list and spin up a node each for each record and send a private state to each node. So here you send Mike, here you send Monica, you have Juan here, you have Prakesh here, you have Dilip here. So you spin up as send requests for each of those instances. You spin up send request for each of those instances. And what send does is that a single send request takes the node you want to go to, which in this case is calculate grade. It takes that. Then it also takes the private state. It takes the private state that you want to pass in. Here we want to pass in the score. for Mike, which is 60. This is one send operation. So you're going to spin up this for each of the records, each of the number of records. You do it dynamically. You spin it up for each of the records, and send is going to enable you to spin up as many instances of this node as you can and pass in a private state to each of them. And at the end of the day, you can take everything and pass it into this final report node, everything here, pass it into this final report node, and at the end of the day, you can generate a full report. You can generate a full student report on this node. So that's what send helps you to do. You map the operations to as many nodes as required based on the number of dynamic instances that you have. You pass in different state values, different values to each of the nodes. It will work on them. Then you can then use your next node to synthesize all those information, to combine, to gather all those information together and prepare your final report. That's basically what send does. It does map reduce for you in your graph operation. And all these instances are going to run in parallel. All of them are going to run in parallel. All of them are going to run in parallel with the private state. And at the end of the day, it will perform the node operation on each of the data that is passed to it. And you can then gather all the data into the state and process them in the next node. How amazing is that? How amazing is that? This is a very, very powerful tool for running parallel operations with different data for each operation. Different piece of data for each operation. You can run parallel operations by mapping to multiple nodes at the same time, but you can't pass in private state to them dynamically. But with send, you can pass in private state to all the instances of the node that are spun up. They both do their calculations, get their values, and you can then bring everything together, your next node. So everything is always clearer and easier with an example. So let us jump into VS Code and see how send works. Now for our demo, we're going to be creating a research agent that takes a topic, splits it into subtopics, and then it will run map reduce on those subtopics to research them, then bring all the research together. So we're going to be using send to do that. Here in VS Code, to begin, we're going to create a new file. We're going to call it map reduce or map reduce send demo.py. And here is where the magic happens. So first, let us bring in our dependencies. Say from typing, import typed dict, annotated, and list. We're also going to be using operator as a custom reducer. So from operator, import add. Then we're going to get our graphing tools from LangGraph. .graph, so import state graph, start and end. Then finally we need to import send, and we can get that from LangGraph. Yeah, LangGraph types. Yeah, import send. So that's our send command. So get send, we have all our dependencies. The next thing we're going to do is our state. We're going to create our state. Now we're going to create an overall state for the graph, for the entire graph itself. So we create a main state, our overall state. Then we're also going to define a private state that is going to be used within the send operations. So for each send instance, we're going to have a schema, a state schema for the private state that will be operating within that send operation. So first, let us create the overall state. Say class overall state. Send in type dict. Then inside here, first is the topic, the main topic that will be passed in. Then we're going to have a list of subtopics that is going to be like a breakdown of the main topic. We're going to break down into subtopics, and that is going to be a list. of strings, a list of strings, and the next thing we're going to have is our research results. Research results. This is going to be the result from the research of each subtopic. Like I said, we take a main topic. That main topic is going to be broken down into subtopics. Then we're going to use send to deploy multiple research nodes that are going to research each subtopic. So each of those research results we're going to have them here. So this will be an annotated I spelled that wrong. Annotated list of strings, and the reducer is going to be our add function from operator. So this is where we're going to be compiling our individual research. So lastly, we're going to have a final report, and it's just be a string. This is the final synthesized result. Now that's the overall state. Now let us define the research state. That's the state that will be operating in each send operation. So let's call it research state. It will also be a typed dictionary. Now the first key or the first field here is going to be subtopic. This is a subtopic we want to research on. So this is a subtopic from the list of top subtopics. This is a subtopic, the single subtopic we want to research. So it's going to be a string. Then we're also going to put in here research results. We're also going to put research results. This is the same research results from here. And it's just going to be we're going to set it as a list of strings. Now these are research results from here, and why we put it here is because we want to inside the node that does the research for the subtopics, we just want to append to the research result. So we get that, and we have our state, and then now we define our nodes. Now the first node is going to generate our subtopics. Now in this demo, we're going to be mocking all this stuff, but these are things that are going to be done dynamically, either by pulling them from a database or doing some processing to break things down, or fetching subtopics through an API, or even using an LLM, using an LLM. So this is something that is going to be done dynamically, but here we're going to be using mock data so that we don't have any sort of dependency. So here we say define generate topics, or let's say generate subtopics to make it more appropriate. So generate subtopics, and for this node, it's going to take overall state, because we're setting the main graph here. It's going to take overall state, and it will get topic. Topic is going to come from our state. Topic. Then let's say we did all the processing, yada yada yada, and we somehow generated some subtopics. So say subtopics, and that's subtopics is going to be a list, and we're going to have a few subtopics here. So let's say for our topic, we want to research the history. Let's say our subtopic is something like quantum physics, something like that. So we want to research the history. Then once again, we want to research the current trends on that topic, and we also want to look at the future of quantum physics. So future outlook. So we'll take a topic and we'll break it down into history, current trends, and future outlook. So we get those subtopics, and now we can update our state by saying subtopics and giving it these subtopics. So these are generated subtopics for us. Like I said, this operation is dynamic, so you don't know how many of it is coming. We are coding it, so we know it's 3, but typically you don't know how many of this is going to come. The LLM, if you use an LLM to process that, it can generate 5, it can generate 7, it can generate 17. If you pull it from a database, you don't know what is coming. If you pull it from an API, you don't know what is coming. So this is the generation step. We're generating the subtopics, Now we need to research each one of them. We need to create a node to research that, but the node would only be able to research one at a time. Then we need to spin up multiple instances of that node for each of the subtopic. Each of the subtopic represents the private state, the distinct states that will be going into each of the node. But let's write out the node first. Let's write out the research node. The research is also going to be mocked. So here I'm going to say define research subtopic. So that's going to be the name of our state. Now this is going to use the research state. Going to use the research state for its operation, and it's basically going to fetch the subtopic, which comes from state subtopic, and our research is going to be mocked as a simple string. So say f, say research findings on subtopic. So here we just assume that we did some detailed analysis. We got some data in there to prove our point, and we got some valuable insights and many more. So that will just be our research. But typically, this is also something that will be done probably through an LLM or through an API. So you probably use a reasoning model to do the research and get the results, then pass it back into state. So here we're just going to return our results. And now we go with research results. Research results. And we're simply going to just pass in results. Pass in the result. And because we're annotating it with the add operator, it's just going to append it here, because here we're calling on the main state. So research results, that's fine. Turn it back into state. So it's compiling it in the overall state for us. So once we have that in place, I need to get out of this function. Yeah, good. So once we have that in place, the next thing we're going to do is create the node that is going to compile all the research results and present it to us. So let's do that next. So here I'll say define compile report. This is also going to take the overall state. And here we're going to combine all our results. I'm just going to say results equals states. All our results are in research results, so that's where it is. Then we're going to build a report. So first I'm going to start my report by just having like a delimiter at the top, say 50 lines. Then I'm going to put a new line here. Then the report itself, I'm going to concatenate a title, say comprehensive research report. New line. Comprehensive research report. Then we concatenate another delimiter here. Okay, put that here, and we then build the report. So I'll say for I in results, for I results in, then let us use enumerate to give the results keys, and it should start from 1. Enumerate. You start from 1. What we want to do here is just append stuff to our report. So append the main report itself. And say f string. Then here we have I. Then we have the results. We just put 2. Oh, no. We just put 2 carriage return characters. Good. And then we'll break out of this and return the final report. Return the final report. So our compile report node, which is the node that synthesizes all the information, that gathers all the information, is going to go into research results where we have been compiling all our research. Then we build a report. We call it a comprehensive research report. We loop over those results and we just add the individual researches to the report, and then we send it back as a final report. Oh, I'm not done with this. Final report is going to be a report. Yeah. So final report. Awesome. So now we have our nodes. Time for our edges. And like I said, you spin up your send requests from a conditional edge, and we're going to be seeing how to do that now. So I'm going to create that conditional edge and call it continue to research. So after gathering the subtopics, the next thing we want to do is continue to research. It takes in state, and for this we need the overall state because we need to be able to access those subtopics. To get the overall state, and inside here, this is where the magic happens. So we create a list of send requests. So we want to send. I like starting with the for statement for this expression. So I'll say for s in state subtopics. So s in state subtopics would like you to set a send request to the research node, which is research subtopic, and give it the state subtopic because it expects a subtopic. If you look at the schema, it expects a subtopic, and that subtopic should be set to s here, which is our s here. So we'll set this. Yeah. So we generate a send request for each of the subtopics that was generated with this conditional edge. So that's all we need to do. This is the map operation. Oh, I'm out of that. So let us get out of this. And now let us build our graph. So I'm going to say builder equals state graph. Our graph state is overall state. So put that here. We got our nodes. So we say builder.add node. Just going to add them with their function names. So one for generate topics. Duplicate that. Then we have two more. One for research subtopic and one for compile report. So that's good. Now we need to define our edges, which is where we're going to we'll set up the entire operation. So first, it's a builder.add edge. Add edge. We start, and first thing we do is generate topics. So we generate our topics. And next thing, we add another edge. After generating our topics, we then want to go to that condition, which is continue to research. So we go to continue to research. And once we do that, all the research topic nodes should end up at compile report. Compile report. And once we're done compiling the report, we can then end the graph. So we end here, and now let us compile this graph. So I'm just going to say graph equals builder.compile, and then we can test this out. Let's test it out. So test the graph. Okay, that's good. So To test our graph, let us define our initial state first. Say initial state. Our topic, let's say our topic is artificial intelligence. That's why we're here. Our topic is artificial intelligence. Then our subtopics. For our subtopics, we have none, an empty list. Our research results is also an empty list. And our final report is an empty string. Yeah, and a comma there. Final report is an empty string. So our topic is going to be artificial intelligence. So by the time it generates subtopics, breaks it down, it's going to be artificial intelligence history, artificial intelligence current trends, and artificial intelligence future outlook. So we have all those in place, and now we can say final state equals graph.invoke initial state. Awesome. Then finally, just as we've always done, print out our final state so that we can see the results that we get from our map reduce operation. So let's save that. And but before let's just print out our final report from here. Let's print out our final report here. Yeah. So do this. Oh yeah, I still have some errors from the last demo. Okay, so we print out our final report from the final state. Let us run this. Python map reduce send demo. Yeah, I hope the demo goes on our side. Let's run this. So we get an error. It says that the value error found edge ending with engine at node, unknown node, continue to research. Interesting. Continue to research. Is there a problem with continue to research? We have a problem with continue to research. Let's see what the problem is. Now research topic. Let's go down, continue to research. Oh. Big. My bad. Also here I am adding a conditional edge. And I'm using add edge. That's a bad mistake. I'm supposed to use add conditional edges. Yeah, add conditional edges. Sorry about that. Add conditional edges. That is what I'm supposed to use here, not add edge. Sorry about that. So let us run this again. Let's clear. Now demo gods, here we plead, and boom, yeah, we get our result. We get our result this time. So comprehensive research report. As you can see, research finding on artificial intelligence history, research finding on artificial intelligence current trends, and research finding on artificial intelligence future outlook. So we've been able to generate a bunch of subtopics, even though we didn't generate them, but most likely you're going to be getting this from a dynamic source and map it to a node that we spin up, like worker nodes. We spin up multiple instances based on the amount of operations we need to perform. At the end of the day, we bring all the information together and synthesize it into a final output. And that's the magic of send. In this video, we're going to learn how to undo errors, transient errors in our LangGraph operations using something called the retry policy, using LangGraph's retry policy system. Now, imagine this. So you have a node. Let's say the graph that we are looking at, the hypothetical graph here, sends an email. So you have a node that collects user input and processes it, transforms it to a standard format. Then you have another node here that prepares the email. It drafts the email, probably even uses an LLM to draft the email. Then we have another node down here that sends the email. It sends it through a service, through a tool that calls an API. It's an asynchronous operation. It calls a remote service, sends an email. So we have from here to, and from here to here. So let's assume this does its operation, connects the user input, fine, everything works fine. This calls the LLM to draft the email. The email is drafted fine. Everything is fantastic. Then when it gets here and it's about to send the email, something goes wrong. Something goes wrong. You want to retry that. It tries to send the email through the service and it gets a 500 error. Something goes wrong. You want to be able to retry that, because API errors, especially the one that return a status code of 500, are transient. They are server errors, so you can handle them. It's not like 400 errors that you know that the problem is coming from you. You're sending a bad request, or you're not formatting the request in the proper way. But if it's a 500 error, you want to retry it, because there might be a network error, there might be some internet issue, there might be some database issue on the server backend and stuff like that, or just something on the network layer. So you want to retry it. And sometimes even the error might persist for a while, say a couple of seconds or like a minute. You want to keep retrying it. You want to keep retrying it, because you can't just leave it. You can't just leave it like that. The operation needs to continue. And this is an error. This is not a code error that it's there. You would have to go into the code to fix it. You can't be retrying the code error. You have to fix it before you retry it. This is something that occurred on the network layer that will be fixed. This is something that occurred probably at the database layer that would definitely pass away. So you want to retry. And that is why we have retry policies in LangGraph. We have retry policies in LangGraph. And by adding these retry policies to your nodes, it helps your nodes to be resilient. It helps them to be reliable, so they can self-heal from issues. So if this node tries to send the email and the service fails, returns 500 error, the node will automatically retry. Probably after like 2 seconds or after 4 seconds, it will retry. Then if it fails again, it will retry again. And you can always set the amount of time that you want it to retry using the retry policy. You can use the retry policy to set a lot of amazing things. You can use it to set how many times you want it to retry, how long between retries. You can even use it to set what errors it should retry on. So it's always good to get specific on the types of errors you want to retry on, especially when you don't just want to retry on every error, because like I said, for a code error, you have to go into the code to retry. So you can't have your system retrying an error when there's an error in the code. That will always fail, except the programmer goes inside and fixes that error. But if it's a transient error, mostly network, it might even be when you're calling the LLM, OpenAI service can fail, Gemini service can fail. You want to retry those kind of errors. And so you can also set errors. You can even define something called a backoff strategy. That kind of expands the timing between each retry. So if you retry after 2 seconds, the next retry can be after 4 seconds. Then the next one can be after 8 seconds. So you kind of define like a multiplier to either increase the time exponentially or constantly. So how do you retry? How do you configure a retry policy? So like I said, a retry policy first has to be done on a node. And if you want to set a retry policy, but let me put this aside. Let's get this aside. Yeah, just stay here. So if you want to set a retry policy on a node, let's say you define your node. Say my node. And it takes in the state and all the yada yada yada. Define it. Then so you have your node. You set your retry policy when you want to add the node. So let's say we have builder, state graph, takes in the state schema. Then when you want to add your node, say add node. You set your node name. You set your node function. Then for your retry policy, you set a retry policy argument. and you set it to the retry policy class. Retry policy class. Okay, put it here. So you set it to the retry policy class. You set a retry policy argument and set it equal to retry policy class. Now this retry policy class can take a bunch of values. You can take a bunch of arguments rather that you can use to configure it. Like I said, you can configure how many times you want it to retry. You can configure the distance or the time between each retry. If you use it this way, it's just going to go with the defaults, which are also good, but sometimes you want to have more control. So let us look at this. Let us look at the retry policy class. I'm just going to put this here. Let's say retry policy and look at some of the arguments that it takes inside its constructor. So retry policy, let's go inside there. One of the most important ones is max attempt, or most common ones is max attempt. It's of type integer, though you don't need to set it like this. You don't need to set it this way. You just said max attempt. But also that is of type integer, and you said to how many times you want it to attempt a retry. How many times you want to attempt a retry? Because you don't want to retry forever. You don't want to retry forever. So you can say like 5. 5 times is good. If you tried 5 times and it's not going through, just raise an error. Just raise an error, and you find out to gracefully address the error. Another one is initial interval. Initial interval. And this is seconds. And it sets how long you should wait before the first retry. Yeah, how long you should wait before the first retry. So you can say once it happens, just wait like 2 seconds first. Yeah, wait 2 seconds first. Then subsequently, probably you can do like one second after that. So that's the initial interval. You can also set a back-off factor, something called a back-off factor. Now your back-off factor is also of the type float. By the way, initial interval is also of the type float. Let me just put that here. Okay. So this is int. This is float. Okay. So back-off factor is also of the type float and is a multiplier for the interval timing. So if you set it as, let's say 2, if you set it as 2, if the initial interval is 2, the next interval will be times 2, so that will be 4. The next interval after that is going to be 4 times 2, which is 8. The next interval after that is going to be 16. That's 8 times 2. So it's kind of like expanding the time that you want to be between each retry. It's expanding time between each retry, because some transient errors can actually take a while. So you don't just want to be retrying after like every 2 seconds, and it will just kind of hit some rate limits. So you want to be spacing out the time, so that you don't DDoS there, or should I say DOS, because it's not distributed. So yeah, the back of is cool, and it's also a float, so you can set it to like 1.5. So back off is a float. Let me put this comma here before putting this. Back off is a float. The next one we're also going to look at is called max interval. Max interval. Now you can set back off, but sometimes you probably don't want it to keep increasing to like let's say 500 seconds or to like 10 minutes. So you want to say, okay, no matter the amount of multiplication that is going on the interval between each retry, it should not be more than 128 seconds. So it's also in seconds. It should not be more than 128 seconds. If it reaches 128 seconds, they just be retrying after every 128 seconds within the number of attempts. All this is still within the number of attempts. So it's not like it's going to go on forever. So this is an int. This is an int. Or it's a float. Sorry. It's a float. The next one is jitter, which is quite interesting. It's a Boolean field, so you can say it's true or false. It's equals. So jitter is Boolean. You can set that to true or false. And what jitter does is that it just kind of randomizes the timing. So even if you have a multiplier that's like 2, and let's say you multiply 2, the initial interval is 2, so then you have a back-off factor of 2. So you say 2 times 2, that's 4. But instead of doing it at 4, it can decide to do it at 4.2 or 4.8. Just kind of stagger the time so that in case you have like multiple nodes that are working with that retry policy, they will not be firing at the same time. They will not be firing at the same time. They will not be trying to retry at the same time. And this is quite important, especially in production, because you want to avoid something called a thundering herd. You don't want like multiple nodes to just be firing at the same time, retrying at the same time. No, you want to stagger them so that they all kind of have like a few gaps between when they are retrying and everything doesn't like raise hell. So we have jitter, and finally we have the retry. Let me put this here. We have the retry on argument. And what this does is that it just sets the errors you want to retry on. It sets the errors you want to retry on. Now you can decide to retry on all errors, so you can just say exception and it will retry on all errors. This is not advisable. Like I said, you don't want to be retrying on errors that you need to manually fix. You want to retry on errors that are transient. Like I said, I always say API errors, network errors, database errors. You want to stick to transient errors. So this is not advisable. So you can also retry on specific errors, like specific errors. Let's say a timeout error. You can say I want to retry on a timeout error. So you can pick a specific error and retry on that error. If you want to retry on multiple errors, then you need to use a tuple. So let's say I want to retry on timeout errors. I also want to retry on connection errors. And I want to retry on rate limit errors, which are all transient. So I can say, I want to retry on this set of errors. So this is how you retry on multiple errors. You can also retry on custom errors from packages. Like, for example, SQLite. If you import SQLite and there's a specific SQLite error you need to retry on, you can simply just say SQLite 3 dot, and you can say I want to retry on the operational error. So when I get any operational error, let's say your node is trying to access an SQLite database, you can say you want to retry on this particular error. And anytime this error occurs, it is going to retry the operation in the node, the query that you're sending to your database, or the connection that you're trying to make to your database inside that node. So that's the amazing retry policy. And next, we are going to look at an interesting example in VS Code. So now that we've learned the theory of retry policies, let us see them in action. We're going to write a simple graph that makes requests to a mock weather API. We're going to write the code in a way that it's the request has a 70% chance of failing, and we'll see how our system retries it until it gets a successful result. So let's start. I'm going to create a new file, and I'm going to call that retry policy demo.py. Inside our file, let's start by importing our dependencies. So from typing, let us get typed dict. Then from LangGraph.graph, let's get our graph tools. So import, dict graph start and end. Then we also need our retry policy. Say from LangGraph, that should be types, import retry policy. Good. Retry policy. Then we're also going to import the random package from the standard library for some of the mock error simulations that we're going to be doing. So let's get that in place. Next, let us create our schema. I'm going to call it weather state. Weather state is a typed dict, and it's going to have 3 state keys, 3 state variables. The first is going to be the city, for which we want to check the weather. So that will be a string. Then we have temperature, which is just part of the weather information we want to get. That will be a float. And then we have conditions, which is just the weather condition, like sunny, cloudy, and stuff like that. So we have this in place. Next, we're going to create a mock class for our API error. So just create a mock exception. We're not going to do anything inside. We're just going to pass. Put some comment here and say simulated error. So this error we're going to raise, and this error we're also going to listen on our retry policy. So we create that, and the next thing we're going to do is to create the node that is going to help us fetch our weather information. And this is the node that is going to try the API, and we'll make it in a way that it has a 70% chance of failing. So let's say fetch weather. Let's go to fetch weather. State. Weather state. Good. Get weather state. Good. So the first thing we do, let's get our city. Get our city. And then let us simulate our requests. So simulate request. We're not going to be making an actual request. We're just going to say that if random.random is less than 0.7. So anytime it falls below 0.7, we assume that it fails. That's the 70% chance of failing I was talking about. So just assume that it failed. Now inside here, we're going to print. Say f string, we'll print a message. I finally figured out how to use emojis in VS Code, so I'm going to put in that here. So I'll say f string, and here we'll just say API call failed for our city. Failed for our city. Then what we're going to do here, we're going to raise our API error. Raise API error, and just say weather API timeout for city. Yeah, weather API timeout for city. So we have that. Let me put a big X here. Yeah, let me put a big X here. Okay, should have failed. Now let's undo the success situation. Let's say I don't need to put an else self. Let's just undo the success here. I'm going to say print, and here I'm going to say successfully fetched weather for city. Then we'll just get a mock temperature, call it say random.uniform. So we can pick within this range and inclusive of the numbers. Put one here. Then for conditions, we can just say random.choice and give it a list to pick from. So here we can say sunny, cloudy, rainy, partially cloudy. Okay, so those are the conditions. That's the temperature, and we're simply going to return both of them back to the state. So temperature is going to be temp. Conditions is going to be conditions. Okay, so that's good. We've set that up. If it fails, if it gives us any random number or random float number less than 0.7, it will just raise this API error and print this. So let's put that there. I need to get out of this function actually. Come down. Good. Now next we're going to create a node that brings all this information together and just presents the weather information. This might be something that you want to do for like a widget, a weather widget. So it just formats the whole thing, adds all the icons and stuff like that, and it just presents the information. But yeah, we're just going to be printing stuff out. So I'm going to say format results, say state. I'll set that to weather state. And inside here, we're going to format stuff. So first I'm going to print F, I didn't put the brackets. So F string, new line, and we'll say weather. Yes, I want an emoji here, so I'm going to just come here. I think I should have that here. Emoji, so I'll put it here. Yeah, this will be cool. So yeah, we'll say weather report for, we'll get a city. Yeah, weather report for city. I'll say print, and for temperature, going to say state temperature, and yeah, say here, right? Yeah, degrees. Then the next thing we're going to print out is the weather conditions. Print conditions, and I'm going to say state conditions. I'm not changing anything in state, so I'm just going to return it back. Good. Let me do something here. Let me change this X to an emoji. Just go here, emoji. So let's make this a proper X, and if it's successful, let's have an emoji here, and that should be, yeah, check mark. Okay, just to beautify the output. So let's put that here. Going to get out of this function. Good. So now we have our nodes, and we can start building. So say builder equals state graph, and we put weather states. State graph weather states. Then we can add our nodes. Without our add node, I'm just going to be dumping the functions directly inside because I want to give them the same names as the function names. So fetch weather and format results. Now, fetch weather is where we're going to set our retry policy, because that is the one that is performing the fetch operation, the asynchronous fetch operation that we are mocking here. So we want to make sure that whenever it fails, because we've already set it up to fail 70% of the time, or I have like 70% chance of failing, we want to make sure that when it fails, we retry. So let us do that. So I'm just going to come here. Let's do this like this. Let me just do this the proper way. Put the name. Let's come down here. Put the name. Add the function. Be a good boy. Then say retry policy. So we set the retry policy argument. And like I said, we set this to retry policy, the class. And then inside the constructor, we can configure it. So first, we want to give it max attempts. Leave that at 5. After 5 times, it's just fail. 5, then initial interval. Let's set that to 1 second. Let's give it a back off factor. Back off factor of 2 is okay. 2.0. The max interval should not be more than 10 seconds. And let it jitter. Set that to true. And very important, it should retry on our API error. It should try on our API error. So it should retry when our API error is raised. So I have that in place, set that up, because this is the node where the main action is taking place, and we want to retry whenever it fails. So next, let us add our edges. Say builder dot add edge. We start. We go to our fetch weather node. Then I'm just going to copy this a few times. Then from our fetch weather node, nope, not that. From our fetch weather node, we go to our format result node. Then from our format result node, we end. So I don't need that last one. So end everything here. So that's good. Now we can compile our graph by calling the compile method. And now we can test the graph. So just going to say test the graph. That's the graph. And we're going to be testing this graph. We're going to be wrapping it in a try except block, because we might exhaust all the attempts. And once we exhaust all the attempts, we just want it to feel like a normal error. So we're going to be wrapping this around a try except block. So we're just going to say result equals graph.invoke. Then we pass in our initial state. I'm just passing it this way. Pass in our initial state. And for that, we'll say our city should be San Francisco. The temperature should start at 0. And the conditions should just be an empty string. And down here, we can print. Say f string, new line, final results. And since I'm now addicted to emojis, I'm going to put a sparkle here. Yep, just for the flair. Then if we exhaust our attempts, then we'll just catch it as an exception. Down here we can say print new line, another cool emoji to show that everything blew up. And then we can say all retry attempt exhausted. And just talk about the error. Print out the error. Okay. So everything is in place. I think we can run our graph now. With our node, our fetch weather node having this retry policy. Now, when we run our graph, the number of times this message shows up, this API call failed for city shows us the number of times it failed. And we'll see that it will be retrying. So we're going to run it a couple of times just to see what it does in different at different times. So the Python retry policy demo. Let's hope everything works fine. Hit enter. So it failed, then it succeeded. It failed, it retried, then it succeeded. That's not fun enough. Let's try again. I want to fail a couple of times. Oh, this one just succeeded once. That is no fun at all. Let's try again. Fail. Good. Now we're talking. So you see, the time between each failure is expanding, and this has gotten to 4. If it fails one more time, it's not going to retry again. So it's still all attempts exhausted. All attempts exhausted. Now we might have tried this a lot of times. I would never hit this. So it tried 5 times, and you see the gap between each retry was getting bigger because of that backup factor. And at the end of the day, it retried all the time, and yeah, we exhausted our attempts. And you see, and this now it's succeeded once, failed again, succeeded. Awesome. That was cool. So yeah, that's how you use retry policies in LangGraph.